Yeah.
Okay, so now we're live on YouTube. Sorry, I was looking at the chat on Zoom and I forgot to click the go live button on YouTube. So we are here for the summer school on the assumptions of physics.
Okay, shall we get started?
Yeah.
All right, yeah, welcome to the 2025 Assumptions of Physics Summer School. I'm Christina Della, a professor of physics at the University of Michigan. I co-lead the Assumptions of Physics project along with Gabriele Carcassi, also in the physics department here at the University of Michigan. He's the technical lead of the project, and I imagine that many of you are also familiar with one or both of his YouTube channels related to the work of the project. I will be moderating the discussion throughout the school. He will be giving all of the lectures. Please, regarding the discussion, please use the webinar Q&A to write your questions. Feel free to write questions at any time. If I feel that it's an important clarificatory question, I may interrupt the lecture to have it answered right away, but most questions will be saved until the 30-minute Q&A session after the end of each 60-minute lecture. If we end up with more questions than we have time to answer, we might need to prioritize. So please upvote questions that somebody else asks that you would also like to see answered, so that can help me prioritize which ones to address. All right, I now turn things over to Gabriele Carcassi.
Thank you, Christine, for the introduction. I just noticed, of course, that there is a problem. Let's check because it's doing the automatic captions and of course they are put in the live stream, which are gonna cover the slides. And I never have control of these things on Zoom. Yeah, so I have no idea how to stop it. Sorry, guys.
Do you want to turn off the automatic captions?
If you can figure it out how to do it while I talk, that would be useful. And I can confirm live when I see the caption going away on the YouTube stream. Otherwise, it's going to be the annoying caption. Maybe somebody will find them useful, but they're going to cover text from the slides. So anyway. As you can see, this is the first time that we're doing the school with these tools, so there is always going to be some snafus. And Christine already said everything, so I think I'll just go into the material because I don't like long introductions. So, oh mio Dio. Okay. Sorry, again, another problem. There you go. Okay, so welcome, and for the first session, we are going to have an introduction to our reverse physics approach. But before that, we are going to give you an introduction to the assumptions of physics projects, in case you do not know what it is and what it's aims at. So the main goal of the project is essentially to identify a handful of physical starting points from which the basic laws can be rigorously rederived. You might have noticed, if you studied physics, that the good old theories started with laws of mechanics, laws of thermodynamics, of physical principles in special relativity, and then modern physics started becoming more and more mathematical, where we just say that we have things like Lagrangians, things like Hilbert spaces, and we don't know where they're coming from. And I think that basically that makes the whole understanding of the physics opaque. So what we want to do is essentially go back to the good old days in which we have physical premises as the starting point, so that we know exactly what our theories are about. So one of the things that we want to be able to say, for example, that the assumption of infinitesimal reducibility recovers the classical state. That is, you can imagine to have a ball, you can throw the ball and study the motion of the ball, or you can take a red marker and make a red dot on the ball and throw the ball and study the motion of the red dot. And so the ball, we can say that it's reducible in the sense that studying the whole of the ball is equivalent to studying all the possible red dots that we could put on the ball. And it's infinitesimal reducible if those dots can be made arbitrarily small. Now, the idea is that with this assumption and a couple of others, you are going to recover the classical mechanics. So the classical state really has bundled in this idea of infinitesimal reducibility. On the other side, we can say that the system is irreducible. So for example, we have an electron and we can produce the electron, scatter them, study the electron, but we can't take a red marker and make a red dot on the electron and then study only what the red dot is doing, because the idea is that when we're interacting with the electron, we interact either with the full electron or none of the electron. And this inaccessibility about the internal of the system makes it a quantum system. This is the assumption of irreducibility. And so the idea is that we want to recover the Hilbert spaces and quantum mechanics based on that assumption. So those are basically the thing that we'd like to say at a high level. And then, of course, the issue is that if you really want to do it properly and understand exactly how everything works, you have to do it at the level of the mathematics and also the most fundamental level of the mathematics, because if you don't know what the lower level of the mathematics are saying, you can't know completely what the upper level of the mathematics are saying. And so we want to be able to say something. If science is evidence-based, then a scientific theory must be characterized by experimentally verifiable statements that have a test associated with them. And then we want to show that under very minimal assumption on these logic of experimentally verifiable statement, you recover topologies in sigma algebra, which are the more fundamental layer of the mathematics that we use in physics. So that's kind of the idea, and then we have to go through all the stack and do everything. So what happens, and it should be clear by now, is that we don't follow the standard approach that people have in the foundations of physics. Typically, the standard view in the foundation of physics is that the goal of physics is to find the true law of the universe, what actually happens, and what are the fundamental constituents, and sort of how the universe works. And so the goal of physics is to find this theory of everything that explains all the forces, that tells you exactly what are the pieces, that gives you some kind of ontology, that gives you the perfect description of the universe, and it's going to solve all these problems that we have in the foundation, right? And there is a sense also on the people that work on these theories that's the real physics, that's a real stuff that we actually do, and everything else is kind of an approximation, and it's sort of some lesser physics. And we don't subscribe at all to this. So if you are looking for a theory of everything from us, so that you're going to be severely disappointed, because we have this different perspective because of what we have found. So we have found that, again, experimental verifiability recovers the mathematical notions of topologies in sigma algebra, that geometrical structures are equivalent to entropic structures, as we will see, that Hamiltonian dilution is equivalent to assuming that the system is deterministic and reversible, that it's isolated, and that it's described by independent degrees of freedom. And if you add this kinematic equivalence assumption that we'll see later, you also recover the massive, that you're studying massive particles and potential forces. So the idea is that from this experience, we saw that it's really the physical requirements and the assumptions that drive most of the theoretical apparatus. So it is what we put in the theory that we find in the theory. And so this kind of contradict, or it's at odds with the idea that these theories are describing the true law of the universe, and that's what we are going to do, because the productive view for us is to say that physics gives us a bunch of models, different models that can be empirically tested, and therefore for us is just the goal, the true goal that we have is to clarify under what assumption and what conditions those models actually are going to work and give the correct prediction. And so this is our view for the foundation of physics, that essentially we have to construct a theory of physical models, and then every theory that we have, classical mechanics, quantum mechanics, thermodynamics, field theory, is just a different physical model that you're going to use in different cases. But all physical models are going to have something in common. Like all physical models are going to talk about experimental verifiability. They're going to talk about states and processes and so on. And so the idea is to construct a general mathematical framework in which those things can be well defined, and the tools are the same for all theories. Like in mathematics, you use set theory, and you use set theory regardless of whether you're doing algebraic topology, or, well, maybe you use category theory. But anyway, there is a substrate of things that are common for all the mathematical theories that you're using, and then you go and specialize. So maybe you have sets, and you have topologies that are topological spaces that are sets with added properties. You have groups that are sets with other properties, and then you can have topological groups that sort of put the things together. So we want to have a structure like that for physics as well. We want to have a general theory where there are states, there are experimental tests, and so on. And then you add specific assumptions, and with the specific assumptions, you are going to recover classical mechanics, quantum mechanics, and thermodynamics, so that you can truly understand how these things work and what they're described. So that's basically the overall idea. And how do we do that? Well, we have developed, let's say, two techniques, two approaches to be able to reach this goal. The first we call reverse physics, because it kind of rhymes with the approach in the foundation of mathematics, which is called reverse mathematics. In the foundation of mathematics, we have this approach that instead of taking a theorem and sort of going forward and understanding what can you prove from a set of definitions, you basically go backwards and you find the smallest set of axioms that you need to sort of define and prove the theorems, and that basically gives you an insight on the structure of mathematics itself. And so what we want to do is essentially start from a physical theory as they are described right now, typically with mathematical tools, and instead of going and making predictions and finding things like, for example, in quantum mechanics, a lot of people try to understand quantum mechanics by looking at entangled system and its special cases. Instead, we will want to go backwards. We want to go and find our smallest set of assumptions required to really derive the theory. So that's one of the approaches. It's an approach that sort of comes from the top, from the theory, and goes down. And then we have another approach, which is called physical mathematics, that is bottom up. You start from scratch and rederive all the mathematical structure from the physical requirement. Again, the idea is not to just set any type of math without knowing what it is. We want to start from the physics that says these are the things that we're describing physically. Then we are going to come out with some physical requirements based on that idea of what we're trying to model. That means that we already have a semantics that is very clear, because we know from the start what is it that we're trying to describe. And then we take these requirements and we turn in an encoding in mathematical frameworks. And that's what we call physical mathematics. It's mathematics because it's going to be real mathematics like mathematicians would like to see it, but it's justified for the physics, and it's mathematics that is sort of developed from scratch to know that it is physically meaningful and physically relevant. So for the purpose of this section, we are going to look at reverse physics. And I just want to give you a sort of a sense of how this reverse physics approach, so that you sort of can have some type of general idea. And the general idea, I think it's just better to see it done, and so that you can sort of get a sense. So first of all, we can see a set of results that we have for classical Hamiltonian mechanics. So as I said before, we need assumptions, and one of the assumptions here is the assumption of determinism reversibility, that the system undergoes deterministic reversible evolution, meaning that if I specify the state of the system at a particular time, then I can tell you what its future is and what its past is, right? So that's telling you what's happening now. I'm telling you also what happened before and what's happened after. And what, under this assumption, we are going to have states, and we're going to have some evolution of that state that is given by a displacement field. So at every point, we are going to know in the infinitesimal time step where are we going to go. And assuming deterministic reversibility is equivalent to say that the displacement field is divergenceless, meaning that if we take an infinitesimal region, as many states are going to go in and as many states that are go out. So no state sort of disappears or appears during going through evolution. What happens is that this is just one way to specify this assumption, and there are 8 equivalent ways. So This is one of the things that we like in reverse physics, is not just seeing things in a particular perspective. So there are a lot of people that like information theory, and then they want to turn all of physics in some sort of information theoretic theory. And we don't want to do that. We say that information theory is going to be important. For example, determinism reversibility is equivalent to conservation of information entropy. But we don't just want to have that perspective. We want to have a perspective from statistics, for example, that the evolution conserves the uncertainty of peak distribution. If you have a distribution that it's very peaked and it goes around in phase space, then the uncertainty of that is going to be conserved. Or we want to be able to say that the evolution is thermodynamically reversible. And again, we're going to see that this is equivalent to the reversibility in terms of maps and conservation of number state back and forth. So it's very important for us that we have as many insights that are equivalent as possible, because it allows us to understand deeper what the theory is describing and have a better understanding of what's going on. So this is one assumption, the assumption of deterministic and reversible evolution. And then we also have the assumption of the system is describable by independent degrees of freedom, which means that the variable that describe the state can be divided into groups that have independent definition, units, and count of state. And again, this same assumptions can be implemented in different ways, can be implemented in terms of information theory. Again, the system allows information independent distribution over each degree of freedom, can be implemented through statistics. The system allows statistical independent distribution for each degree of freedom. And again, the idea is that you can sort of mix and match any of these assumptions from one side and from the other side. And if you pick one on one side and one on the other side, you are able to recover this mathematical formulation in terms of symplectic structure, Poisson brackets, or the curl of a rotated displacement field as a lowercase. And then you can find that these are equivalent to, this mathematical formulation are equivalent to Hamiltonian mechanics. And so now the same equation that you might start and are given to you when you study physics that are very cryptic, now you have the combinatorics of 4 times 8 ways of looking at them plus these other 3. And what happens is that when you're studying a physics problem or you want to get intuition, you can use the hat that mostly that is most useful for understanding that problem. And so this is what we are going to do. We are going to ask a question. We have in quantum mechanics this idea of an uncertainty principle, and one of the things that comes out of reverse physics that it's really very productive to not just look at one theory, but look at the collective of theories in physics and try to understand what is different and what is the same. And so the question is the uncertainty principle really a feature of quantum mechanics alone, or can we find something that is similar in classical mechanics as well? And so we go back to our set of equivalence assumption. We're talking about uncertainties, and we have seen here that there is this condition that the evolution conserves the uncertainty of peak distribution is equivalent to this assumption of determinism and reversibility. Okay, so what does that mean? How does that work? So the way that you can describe uncertainty for a single degree of freedom in a phase space is through the use of the covariance matrix. So the covariance matrix is essentially a set of expectation, and the covariance between two variables is the expectation of the product of each variables minus their expectation value. So it's the product of how far they are from their corresponding expectation values. And if the values are the same, so this would be position and position, what you get is just the variance. And so this is going to be the variance for momentum. And if the two variables are different, you get what is called the covariance. And the covariance of QP is the same as the covariance of PQ. So this is a symmetric matrix. Like it's everything that is off diagonal, it's going to be symmetric with the transport. And now, of course, a good coordinate independent way to characterize this uncertainty is through the product, through the determinant. And so the determinant is just the product of sigma q squared, sigma p squared minus the square of the covariance. And we can call that sigma squared. Now, if the distribution is peaked, meaning that the area that this covariance matrix that corresponds to this is very small, then you can assume that the flow is linear, that your distribution is linear, is moving through seeing a linear field. And then in that case, then the covariance matrix transform linearly with a Jacobian on both sides. So you have the covariance matrix at time t0, you have the Jacobian on both sides, and that's going to be the new covariance matrix. And so you have this relationship between sigma q sigma p minus the covariance and the original uncertainty. And you can see that this, and this is going to be the original one. So it's the same for the whole evolution. So this kind of tells us that there is some type of boundness on the uncertainty, because if we have this original uncertainty, the covariance can only be positive. And so this number, the sigma q sigma p, can only be greater or equal than the product of the covariances that are in the original. Okay, so this is kind of like an uncertainty principle, because we have an uncertainty and there is a lower bound on the uncertainty, but it's very different from the one that we have in quantum mechanics, because this sort of depends on the initial conditions. And so can we do something better? And the idea, well, we can go back and see all the things that we had before and find something else that might be useful. And we have this in terms of the information entropy. The evolution conserves the information entropy. So why don't we go and look at a little bit at that and see what we can figure out. So the first problem that we have with information entropy is that this is the formula is minus the integral of minus rho log rho. And this rho is a probability density. So it has units of probability, which is dimensionless, over units of phase space. And we cannot take a logarithm of quantities that have units. That doesn't make any sense. And in physics, a lot of the time when we have this problem, we just bury our head in the sand and we just go forward. And the point of reverse physics is saying, no, we have to fix all these issues of units, because if we don't fix them, we're never going to have a chance to actually understand what's going on physically. So let's go and try to fix this problem of the logarithm. How do we do it? Well, in principle, we need to multiply this rho by a constant. And this constant is going to have units of areas in phase space, because it has to sort of counteract the density of rho. So what does this h mean physically? Well, suppose that you have an area of phase space that is h, and you take a uniform distribution. A uniform distribution will be the inverse of the volume, 1 over h. And if you take 1 over h, put it here, you're going to have logarithm of 1. Logarithm of 1 is 0. So it means that a uniform distribution over an area of h has 0 entropy. And so we have now a good physical representation for this constant. We say that h represents the volume of phase space that corresponds to the 0 entropy for a uniform distribution. And we introduce this constant without knowing that there is a quantum mechanics, without knowing anything. It's just the constant that sets the scale for 0 entropy in classical mechanics. That's it. Okay? So what can we do with this? Well, what we want to do now is to plot the entropy against the uncertainty. So we have fixed our units. And what we want to do now is to have a graph where we put the uncertainty on this axis and the entropy on the other axis. And what happens is that the Gaussian states maximize the entropy for a given uncertainty. So if you pick an uncertainty, let's say 5, and you go up in entropy, at some point you are going to hit a Gaussian, and that Gaussian will have the maximum of the entropy for the given uncertainty. So what happens is that all these region is excluded. There are not going to be any distribution here. There are going to be Gaussian distribution on the red line, and all the other distribution are going to be below. And again, if you look at this, this again kind of looks like an uncertainty principle. We have a sigma q sigma p on this side, and that has to be greater of something else. So what we can do is take the exponential on both sides, and we get the sigma q sigma p is greater or equal to h over 2 pi e over e exponential of the entropy. And we have an h over 2 pi, so let's call that an h bar. And now we know that the product of the uncertainties, the product of standard deviations, have to be greater or equal to h bar over e times the exponential of the entropy. And so the Hamiltonian evolution conserves the entropy. And so now we have, we see that entropy puts a lower bound on the uncertainty. And now this is not just a property of the initial condition, it's really a property of the state, because the entropy is a property of the state. So given a state, you are going to have to satisfy those bounds. So it's a little bit better than we had before, because there is no time correlation. Like we're not looking at some initial time. We just look at every time this has to be true. But again, it's slightly different than an uncertainty principle that we have in quantum mechanics, because in quantum mechanics, we just have a constant. There is no dependence on the state. So we need something that bounds the entropy for all states. So we're looking for some other principle, some other idea that says, okay, there is a lower bound on the entropy, and this is the maximum that you can do. And if you think about a couple of minutes, there is such thing already in physics, and it's called the third law of thermodynamics. There are many different formulations of the third law, but one of them is that there is an absolute zero of entropy that is reachable only at a zero temperature for a perfectly crystalline substance, where basically nothing is moving in some sense anymore. So if we now take the third law of thermodynamics and combine it with the entropic conservation that we had before, then we do have a lower limit, and we just take the exponential of the entropy. The minimum entropy is 0, so the exponential of 0 is going to be 1, and therefore now sigma q, sigma p, the product sigma 2 sigma p has to be greater or equal than h bar over e. And we call this the classical uncertainty principle. And again, you can see here in the graph what happens. We have all these region that is excluded by the Gaussian bound. There is all this region that is excluded by the third law of thermodynamics. So the best we can do in terms of entropy of uncertainty is this point here, which happens to be a Gaussian state. And so what we have then is that if you compare the two theory now, they look very similar. They both have an uncertainty principle. Quantum one is h bar over 2, while the classical one is h bar over e. And what happens in quantum mechanics is that you already have the fact that you are following the third law of thermodynamics, because in quantum mechanics, a pure state have zero entropy, and you cannot go below. So quantum mechanics is already incorporating the third law, while classical mechanics is not. That's sort of a difference that it's clearly there. But then what you can see here is that this, the blue one is the plot for the classical bound for the Gaussian bound, and the quantum one is this red one. And you can see that they already become very, very similar, even when you are in this range, right? So that basically what happens is that these two constants are actually going to be the same, such that when you go at high entropy, which high entropy here even just means a couple of units, this Gaussian band is actually the same for both theories. So there is sort of a better reason to way to understand the uncertainty principle, both in classical mechanics and quantum mechanics, and quantum mechanics, as a bound coming from the entropy. It's the lower bound on the entropy that drives the bound on the uncertainty. And we can even be sure that that's the case in quantum mechanics, because this exponential of the entropy actually is a very important quantity that is called entropic volume. And there is a stronger inequality that you can find in terms of the entropic volume. A stronger inequality means that if you assume this inequality, you are going to be able to derive the other inequality, but it's not going to be the other way around. So this equality is stronger than this other equality. Okay, so that's basically the result that we can see while again playing around with reverse physics and trying to put all these ideas together. And of course, one of sort of the where does this lead us is that it leads us to this conjecture that I had for a number of years. So suppose that the lower bound on the entropy is the only difference. So we know that is a difference, that classical mechanics does not have, in principle, a lower bound on the entropy of distributions, while quantum mechanics has, right? So that's a difference. Now, suppose that we say that that's the only difference, right? Then it should follow that once we go at high enough entropy, we're very far from the lower bound, then classical mechanics and quantum mechanics should start looking very similar, because we are far away from the regime in which we clearly have the only difference that we assume. And so for a long time, I had this conjecture that I didn't know how to prove. So last year, I started this channel here. And one of the first videos that I posted, actually the first video that I posted, was this conjecture. That is the classical mechanics, the high entropy limit of quantum mechanics. What happened a month and 10 days later is that an atomic physicist from Vienna contacted me and said, "Oh, I saw this video. Have you considered using these techniques?" And so we started chatting. It turns out that he had the complementary background that I needed to actually prove this thing. And in November, we came out with a preprint that actually shows this result. And so this is kind of one of the problems that we have in this project, is that we're trying to combine all these perspectives together from different sides. And of course, not any single person can have competence in all these different areas. For example, I didn't have any competence in quantum mechanics on phase space, Wigner function, QCMQ, and all that things. He had, and he taught me the things that I needed to do, and I consulted with him and other things, and we were able to write this paper together. So this is kind of why I'm doing this school, why I have this channel. I strongly feel that we have to create some kind of community around these ideas to sort of explore the full power of these approaches. So let me now give you a little bit of an idea of how this works. It becomes very technical, so I'll just give you some sort of a higher level understanding. So what we're essentially looking for is a map that increases the entropy of all mixed states, all the sort of the probability distribution in quantum mechanics. And it does it in a way that a level set of the entropy, so all the mixed states at the same entropy, are mapped to a bunch of other states at the same entropy. So we map levels of entropy up and up in terms of all possible states. And what we also want to have, that a unitary map between two states here becomes a unitary map here. So if we have a deterministic or reversible evolution between two states, then we apply the map that becomes a deterministic and reversible evolution on the new states, right? And that's what we want to do. We sort of want to take the whole states of mixtures and bring them up to high and high entropy and study what happens there. Now, in classical mechanics, this is very easy to do, because as soon as you say, I have a map R that takes a probability distribution, gives me another distribution, and I want this probability distribution to be increased by a constant, what happens is that that constant factor is going to be the logarithm of the Jacobian, and the Jacobian has to be the same over all the transformations. So the only thing that you basically are doing is stretching out phase space. And again, in classical mechanics, this requirement of the map is the same requirement of asking that the Poisson brackets remain, gets this constant in front of it. Now, in quantum mechanics, this is too hard to do. I don't know how to do it. So we take as a definition of a stretching map this idea that we apply the map to two observables, and the commutator gets rescaled. And we're going to call a pure stretching map something that essentially takes x and p and stretches them by the square root of the factor, such that when we put them together and put it here, we are going to have a lambda. Now, of course, quantum mechanics is a little more complicated, because we have the ordering to take care, things don't commute. And then what you can do is, by just assuming that this becomes an infinitesimal transformation, then it has to follow the Lindblad equation. If you know what it is, it's the equation for open quantum system. And then you can find that the jump operator has to be the antilateral operator, whatever it's called, and that gamma here, it becomes this lambda, right? So essentially, you can find the transformation that actually takes this thing up and then find that all the other sort of equivalent transformation are there connected by a unit. So this is complicated to see, but we can see it in a much simpler way that it's in some sense less physical and in some sense more intuitive. So instead of saying I'm going to go up in entropy, I'm going to stay where I am, but I'll take the pure states that live at 0 and bring them down. So instead of going up in entropy, I'm going to take the reference and bring it down in entropy. So the entropy difference is going to go to infinity in the same way that it was going there in the real limit. But mathematically, it's a lot easier to understand what's going on. So what's going on if we are increasing the entropy on the transformed, then what happens is that the target is the one that is going to get the factor of lambda. But if we keep the transformed space the same, and we want to start from a space that is at lower entropy, what happens is that the lambda is not going to be here, it's going to be on the original states as an inverse. So you're going to have a lambda here that it's down, and this lambda is going to go to infinity, and will make this commutator go to 0. Or in another way, you're going to say that the h bar over lambda is going to go to 0, or mathematically, you can just say that the h bar goes to 0. And this essentially recovers the group contraction, which is a standard way where mathematicians recover the classical limit. And this works, and it makes both the classical limit of quantum mechanics and the non-relativistic limit of relativistic mechanics look mathematically the same, because it's just a group contraction in both cases. You have some algebra that has a parameter, and you're moving that parameter either to infinity or to 0, however you want to look at it, and you are changing the forming the state, and in the limit you get classical mechanics in both cases. So for relativistic mechanics, if you go to low speed, it's like mathematically you're taking the speed of light to infinity, not because the speed of light goes to infinity, but your speed is so small that the speed of light looks so big to you, and you might as well say that it's infinite. So in the same way, for quantum mechanics, you are going to be able to say that if we go to high entropy, the entropy and the uncertainty, the related uncertainty of the pure states becomes so small that you might as well say that, again, the uncertainty goes to 0 and the entropy goes to minus infinity. Now, what happens here also, this allows us to understand better what the correspondence principle is doing. So Dirac assumes this correspondence principle that you can take Poisson brackets in classical mechanics and put in commutators to get quantum mechanics, and so the idea there, okay, you're doing something mathematically. What is it that you're doing physically? Well, in physically, we saw what's happening. We are looking for a theory that puts a lower bound on the entropy, but recovers classical theory in the limit. And what is a mathematical result? The mathematician tells me it is true, that there is only one way to do it. If you're doing it in phase space, the Moyal bracket, the one used in quantum mechanics for phase space, is the only one parameter group deformation of the Poisson bracket. So if that's if the math corresponds to what we're saying precisely, then we are also saying that there is only one way to do it. There is only one way to quantize the theory, and quantizing a theory in this constant means putting a lower entropy, a lower bound on the entropy, and that's it. There is nothing else, because there is only one way to do the thing that we are actually doing. What is also interesting here is that there is no mechanism for all of this. So in the same way that once you do the classical limit for relativistic mechanics, there is no mechanism for which the speeds are low. Like the speed happened to be low for a specific problem, so you can make that approximation. So the same type of reasoning happens here. There is no mechanism for which quantum states become, in a sense, classical. No, you just have to go at high entropy. And once you go at high entropy, if you are at high entropy, for whatever reasons, you are going to get this effect, and you can make this approximation, and you're done. Right. So that's it. So it makes this classical limit very nice. So another thing that we see here is that entropy is it seems to be playing a very important role in both classical mechanics and quantum mechanics. And again, we threaded all these ideas by going back and forth in the spirit of reverse physics, where we are encouraged to go back and forth to understand these things better. But how far can we push this role? Right? Because entropy is always seen as something that applies to statistical mechanics, not something fundamental that it's inside mechanics. So is it that the case? Should you think as entropy as a sort of a derived quantity as we're pushed to typically by learning physics, or there is actually much more a fundamental role that entropy is playing? And so one of the things that we can show, and I actually have a video about it already, is that the geometric structures that we have in classical mechanics are equivalent to exactly the structures that we need in information theory to be able to define entropy and all these related ideas. And there is just a translation in between. And this is kind of the problem that we have right now, that the mathematical structure that we have are sort of completely disconnected from each other, and you can't see that they're actually the same things. If you're doing a geometry in a phase space in classical mechanics, you use symplectic manifolds, which is a whole different theory. If you're doing probability, then you're going to use measure theory, and information theory. It's something that sort of takes some ideas from measure, but then you have to be able to have to do some other things, right? So this is kind of the problem, that the two theory seems to be disconnected. Instead, they're joined at the hip. What happens is that in a symplectic manifold in phase space, so the areas of phase space are defined by what it's called a symplectic form. And the geometry is given by the symplectic form in terms of areas and volumes, and that physically count the number of configuration and number of states. And of course, there is a link between the entropy and the count of states. If I have a uniform distribution over U, then the entropy of that uniform distribution is the logarithm of the count of states. So if I give you the geometric structure and then I have some definition of probability on that structure, I can go and derive the information. I can go and derive the probability, because probability of uniform distribution is 1 over the measure, and the information entropy is just the logarithm of the measure. But it works the other way. If I didn't give you this metric, this symplectic form and the notion of areas, and just I give you all the distributions and their entropy, since the logarithm is an invertible function, you would be able to go back and forth. You would be able to say, okay, this distribution is uniform around this region. I look at the entropy, I do the exponential, and now I know the area. So you can go back and forth. So either you give me the geometric structure or you give me the entropic structure. And when you give them one, you exactly given me the other. You gave me no more information. You can go back and forth. And the same happens in quantum mechanics. And in quantum mechanics, we don't have regions and volumes and so on. The geometry is defined by an inner product. And the square root of inner product gives us probability. And if you have two pure states and you give and you prepare unequal mixtures of those two pure states and you look at the entropy, then the entropy is a function of the probability of the transition between the two states. And it's not just a function of those, it's an invertible function. So again, you can give me all pair of states and give me their inner product, or you can give me the square of the inner product, or I can give you the entropy for all the equal mixtures of any pairs of states, and from that you can recover the square of the inner product. You can recover the structure that you have on the projective Hilbert space. So this thing that the geometry is entropy works both in classical mechanics and in quantum mechanics. So entropy is really a more fundamental quantity that you think, because it's equivalent to giving these geometric characterization of both classical mechanics and quantum mechanics, which are the structure that you need to define your Hamiltonian evolution. So if this is true, if geometry is entropy in both classical mechanics and quantum mechanics, then it is not true that thermodynamics and statistical mechanics are built on top of mechanics, that you first have two mechanics and then you add some other structure above, because the structure that you gave me, the geometric structure of classical and quantum mechanics, is exactly the thing that I need to define the entropy and everything else. and Hamiltonian mechanics is conservation of entropy, and therefore it's sort of the same thing. So really, we should think of mechanics more as the ideal case of statistical mechanics. It's basically we're taking all the possible distribution that we have, and since there is linearity in terms of the statistical distribution, if I know that a distribution is made of two distributions, is the sum of two distributions, I can move the components, and I know how the whole moves. So if you know how to move around, how to evolve the distribution with the lowest entropy, then you know how to move deterministic and reversible everything else, because everything else is linear. And so the pure states of both classical mechanics and quantum mechanics become that. They are the best state that you can hope to prepare. And in classical mechanics, you assume that you can prepare them with infinite precision. And quantum mechanics is more realistic. It says, no, you can't prepare things with infinite precision because there is a lower bound on the entropy. And that lower bound on the entropy sets the scale of what you can actually control in terms of the precision of your states. So this is sort of a sort of a overview that I hope it gives you the idea of how much nicer, meaningful, and insightful is this way of proceeding. That extracting principle as assumption behind the laws gives you more solid intuition that cuts across all the fields, and it gives you more insights and results. Like we can start being driven by physical ideas much better than just mathematical ones if we have these shortcuts in our brain of the intuition of how to go from one to the other. And again, the way that we do it in reverse physics is to strive to have multiple equivalent starting points. So we can say that we have Hamiltonian mechanics, entropy conservation, and uncertainty conservation. Like all those things turns out in some precise sense to be all equivalent. And this is what we should be doing more instead of looking at one thing and pretending that everything is that one thing. Have these different perspectives that sort of complement each other. We saw that every detail counts. Somehow dimensional analysis has fallen out of favor, and a lot of new theories that we have are just a bunch of math, and then you fix the units later somehow. But we saw that there is meaning. In fact, another thing that I'm not going to show here, but I did sort of the same work on, let's say, the Dirac equation in quantum field theory of putting the h bars where they need, the c's where they need. And you can understand that equation a lot better once you do that, because now you know what those operations physically means, and you get physical insight. And the other thing is that you should always be open and ready to reinterpret and recombine results. Like this picture that we have right now is the product of an evolution of a bunch of ideas that we tried and said, oh, this works. And then you realize 3 months later that there is something better. And so you always have to be able to take these things from different areas and put them together. And with that, I want to close with sort of a kind of a message that if you are working on foundational questions, you should always have in the back of your mind. Is that you can't really judge arguments you're not familiar with, either yours or others. So many insights that we have had in reverse physics, they basically started as tricks. Like I knew where I wanted to end. I had an idea of where I want to start, and then I start making an argument, right? And these arguments at the beginning, they seemed like completely ridiculous. And it's not, they seem ridiculous because you're not used to making them. And then what happens in some cases that some of them are ridiculous and you throw out, but some others, you think about them more and you find the connections and they become less and less ridiculous as you go through them. And that's kind of the point, is that at the beginning, you are so unfamiliar with our reasoning that you can't see whether there is truth to it. And so that happens to not just the arguments of other people, even yours. And so the point is that a superficial understanding of our argument does not allow you to see the potential connection to other things. And so you sort of have to keep this preposterous argument in your head enough to really see whether it makes sense or not. You're not going to be able to judge it at first. And conversely, there is the other effect. If you are very familiar with a way of reasoning, that way of reasoning is going to prevent you to see the merit of an unfamiliar argument, because your brain paths are always going in the same direction and they're not going through the other direction, so you're not going to be able to see how things work. So the best way to approach it that you should have is essentially to remain playful and try things around and see what happens, and never be attached to your ideas. In fact, it's much better if you just say, these are not my ideas, these are just random rocks that I found on the street, and this rock is nice and this other is nice, and if I find another one, I'll just throw it, because they're not my rocks, they're just the things that I found. Okay, so we can now wrap it up. So assumption of physics is a different approach to the foundation of physics. We don't have interpretation in the standard sense. We're not going to try to find a theory of everything. We just want the physically meaningful starting points from which we can derive the laws and the mathematical framework they need. And in this setting, physical theories are models. They're not true in some objective sense. They are useful in some cases where the assumptions underneath the models are somewhat verified. And so the goal is to clarify exactly what the realm of applicability of each model is. And what we found, to our surprise, is that most of the time, the realm of applicability of the model is the model. Once you specify these are the conditions in which the models apply, you find the physical theory. And so that means that in a physical theory, there is no more than the assumption that you put in. And whether a physical theory applies just means whether your initial assumptions are approximately verified in practice now. So we have this approach called reverse physics, which is basically whose goal is to reverse engineer the principle from the known laws. And the problem is that the current laws are given through mathematical structure, which make it hard to understand what the physics is. And so we have to find physical principles and assumptions from which we can derive the laws so that we can know what the laws are about. This starting point must have a clear and intuitive meaning. For the majority of physicists and engineers, there are a lot of what are called reconstruction of quantum mechanics in the literature. And the problem is that a lot of the time they require mathematical things that you have no idea where they come from. So there is one, for example, that you say, okay, all measurements are probabilities, and then you have states, and somehow the quantities that you need to define the whole sphere are the square of the number of quantities that you can measure at the same time, right? Why? And of course, then people try to justify these things, but it's not something intuitive and clear that physics would have. Instead, if we can say that the difference between classical mechanics and quantum mechanics is just that we have a lower bound on the entropy, well, if you're doing statistical mechanics, which is required anyway when you're doing actual experiment, because you have to sort of think about statistics, you have a clear understanding of what the difference is. It's a lot more intuitive. And so the goal, which of course is not realized, and that's why we needed to build a community of it would be seeing that all the different results that you would have that are different in classical mechanics and quantum mechanics make sense under the light, and in fact they can be recovered in that sense, in the same way that special relativity is just the fact that the speed of light is invariant, and that is sort of the cause of everything else. And another thing that makes it sort of this approach shows us is that it's very productive to investigate physics as a whole, instead of saying, oh, quantum mechanics is fundamental, therefore I only need to study quantum mechanics and then I'm going to understand everything, or I just need to focus on a theory of everything and then everything is gonna be fine. You're going to lose a lot of insight if you do that. There are, as we said before, some sort of requirement that all physical theories must have, and if you can understand how those relate to each other, then those are going to be there in all theories, and it gives you a much better sense of the physics as a whole than just saying this is the one true thing that is more fundamental. I should only worry about that. So as I said before, this needs to be a collaboration between different things. And the reason why I'm able to do this project is because in the past 10 years, I made it a point that I should be able to learn enough about every different single piece of math, physics, computer science, and statistics and whatnot that we need for the project. I need to learn it enough such that I can go to an expert and talk to them in their own language so that I can understand their perspective and try to merge all these things. And of course, I can't be an expert in all of that. And so the only way, as I said, to really make a dent in this problem of setting the foundation of physics on good grounds is to be able to create a community around it. And I have no idea how to do it because it's very interdisciplinary, and the academia really works in little fields that don't quite talk to each other. And so I decided that from the beginning to basically make this an open source project in the style that you have in software engineering, because that's the practice. So our main output of the project is an open access book, which is available through our website, but it's also available on GitHub. And sometimes I get a pull request because somebody made some fixes of typos. Those are the things that make me very happy. So if you want to make me happy, do those type of things. We have one YouTube channel dedicated to publicize, which you probably know, where we put sort of results, but we also have another one where we do the research, where we are trying to do live stream discussion, and I would hope that more people sort of come and participate to these things. We also have a Discord server, so if you're interested in these type of things, just contact me and I will give you an invite. I'm trying to keep it a space where people are interested in discussing real details and not like weird theories that sort of don't even match with the purpose of the project. We want to be extremely focused because we already have so few resources that I can't stay there and the news about the interpretation of quantum mechanics that are not strictly in the scope, and so like that's what I'm trying to do, and so far we have been successful, and so on. And so then I'm always looking for experts to get inside and help. I'm looking always for people to collaborate, and even people in academia that can suggest me which journal and conferences could be sympathetic to this, because again, it's not very easy to do. And to learn more, as we said, we have a project website, their YouTube channel, and our GitHub repository. And I think that's all for this session, so we can open it to questions. Christine, tell me what questions are there.
All right. Yeah, we already have a few questions in the Q&A. So the first one from Carlos is, when you say the classical uncertainty principle is h bar over E, quantum one is h bar over 2, so the classical one is less than the quantum one. You're identifying the classical area h with the Planck constant. What is the reason for such an identification?
So the identification comes because so even in quantum mechanics, h bar is a constant that you go and measure, right? And you measure it because you're going to have some, you can go and measure in this case, we can go and measure the entropy, right, of a classical ideal gas at high temperature, and that entropy is going to have to match with the prediction of the theory, right? And so since these two curves are going to coincide, because they have to coincide because they have to coincide to the experimental data, what's going to happen is these two h bar are going to coincide. Now, the difference in number here basically is telling you that you can squeeze a little bit more precision in classical mechanics than in quantum mechanics, right? And there is a justification, at least intuitive. I like to make it precise. I don't know how to make it precise, so if somebody wants to help me make it precise, it would be great. But this is the intuition, is in classical mechanics, you get this lower limit on the uncertainty, not just because you have a Gaussian, but because the two Gaussians in position and momentum are independent. So you have the full Gaussian is the product of the two Gaussians, right? And you can do that because Q and P are independent variables, and so the preparation of one does not affect the preparation of the other. In quantum mechanics, position momentum are not independent variable in that sense, because any preparation of Q influences the preparation of P. So this lack of independence means that you're not going to be able to have that the joint distribution is the product of the two marginals, like you have in classical mechanics. And therefore, you are going to have something where the bounds on the entropy, on the uncertainty is a little bit higher than you would have in classical mechanics. So again, there are physical reasons of why these things work and make sense. So I hope it made sense.
Okay. Next question we have is from Thomas. The uncertainty principle in quantum mechanics is usually explained in terms of wave mechanics. How does the entropic uncertainty and the wave uncertainty relate?
I do not know. So what I do not know is why if I put this entropy constraint between position and momentum, they become the fact that the one distribution is the Fourier transform of the other. Like I don't see that step. What I know that even in classical mechanics, if you have sort of a distribution of one variable and you make the Fourier transform, so it's all real numbers, you are going to get an uncertainty principle of that type. But the issue is that in classical mechanics on phase space, Q and P are two different independent variables. So there is no connection between one being the Fourier transform of the other. So I would like if there were an argument that said, well, once you make this bound, then you're going to get the wave mechanics somehow. I don't know how to do it. I don't see it.
Okay, somewhat related, mentioning Fourier transforms.
Wait, like if there are comments on the chat, so I'll there's a follow-up on the chat on this. So the classical uncertainty follows the underlying symplectic structure of phase space, the Brown non-equilibrium. Exactly. That's kind of why you have it. And the symplectic structure, as I said, is the thing that gives you the entropy. So those two things are related. I do not know, and maybe they exist in the literature. I personally do not know how these structures would relate to wave mechanics. Like I can sort of see that if we say that the position actually becomes a velocity, and we kind of have a field theory, right? Then this velocity becomes a wave propagation and so on. I might be able to see how this works, but I don't see the details. And in all these things, I'm always I much rather say I have no idea when I don't know the details, even if I'm 90% there, because a lot of the time the extra 10% screws everything up. So I don't want to commit to saying that something, I don't know how something works if I'm not sure that the last 10%. The action becomes the phase in the wave. Again, maybe, I don't know. The action, we'll see it in the next section. I have a geometrical interpretation of the action, and maybe there is a way to link that with wave mechanics. I don't know.
Okay,
next question.
Yep, moving on to the next question from Daryl. My intuition of the uncertainty principle is from noting that position and momentum are Fourier transform variables. If we see two blinking lights with similar frequency for long enough, we can tell the frequencies apart, but we cannot localize it well in time. Yeah. How does this relate to the entropic uncertainty you presented?
Right. So in quantum mechanics, it's the same thing. It's a different thing. And I do not know how the two are related. I strongly feel that there should be a relation, because it would be very intuitive that, you know, it would make sense that there was. But I don't know. My knowledge is limited, so that's why somebody else can work on this, and maybe we can work. We could have an in-depth discussion of this if anybody wants in a live, in which we try to take all these pieces and put it on the table and see if there is anything that fits together. That would be fun.
Want to go back to the chat? I think there's another follow-up from the previous, like in the WKB approximation. I think this is going back.
So I do not know how the WKB approximation relates to sort of the high entropy limit. So I do not know if that approximation is something else completely or not. I'm not I'm not too far, like I haven't looked in the WKB approximation in like the last time I was probably going to be 15 years ago. So I don't know how it would fit in all of this. And again, it's exactly some pieces where somebody can say, okay, I'll have a look at this. So as I said, like I'm describing sort of the approach to me is more important than the result. And so applying the same approach to these other questions, it's something that I'd like to have other people help me. I just had an email, for example, 2 weeks ago for somebody that has looked at the interpretation of the action principle, and he was interested in trying to extend it to the case where you do have dissipative forces, which I thought that it was impossible. And then we discussed a little bit, and actually that there seems to be a way that connects to other things, and then it connects to other things that I'm looking in quantum mechanics, actually. But these are exactly the type of things that I'm looking, like people that then are going to say, okay, let's go and look how these things work.
Okay. Another question from Daryl. Do you see assumptions of physics as laying the groundwork so that it is easier to form new models, such as a theory of quantum gravity?
Yes. I don't think we are going to have quantum gravity until we figure out exactly what are the assumptions that we have in general relativity, the assumption that we have in quantum field theory, understand why is it that they are incompatible, like conceptually, whether the math that we have, make the math that we need for those two theories precise, because I'm not even sure that we are there yet. And then you need to be, because you're going to be able to say, okay, these assumptions are no longer valid. I need to put other assumptions to be able to build the quantum gravity, because I'm going to be in a different regime. I don't even have a sense that the mathematical structure that we currently have right now are going to be working in the assumption and the regimes that we want a theory of quantum gravity work. So it could be that the current math that we have works fine, and you just need to know how. Or it could be that it's totally wrong and we need some different type of math. I don't have the tools to make that evaluation complete right now, because I do not know exactly what are the assumptions built in all these things, because there are some technical problems that I have no idea how to solve. But from the hints that we have, and that we're going to see when we talk about in the open problems, like my hunch is that we don't have the correct structure. So it's one of those. So the problem is that when quantum gravity is going to be a sort of a generalization in some sense of the two theories that we have, and what you can do without understanding things well, you can do interpolation. So if you have two theories and you know that you have a theory that it's in between, you can say, I can make a prediction to that. But if I have these theories, the realm of applicability, this probability, and you have to work here, this extrapolation like that, I don't think it's going to work. So answer is, for me, is a strong yes.
Actually, before I forget, let me come to a practical question that was sent privately to the hosts. So if people do want to contact you to be added to the Discord server, how would you prefer to be contacted? So the info@assumptionsopphysics.org, or your university address, or something else?
Either. They just come to me anyway.
Okay. Okay, so yeah, for example, well, yeah, the Assumptions of Physics website has the email for the project listed at the bottom of the page, which is info@assumptionsoftphysics.org. And it's also easy
And
to,
my email is there in any paper that I wrote, so it's
yes,
I'm not very hard to
look,
find. Also, I have the you know the blessing of the curse of essentially being the only person with my name and last name. So if you search me over the internet, you find me.
okay. So going back to the Q&A, can you explain again how you recover the classical regime from quantum mechanics in the regime of high entropy?
Okay, so I would need a lot more time to do it, but the basic idea is this. So, and I don't know how much physics you know. So in quantum mechanics, you have pure states, which are your typical wave function. Then you have mixed states, which are the density matrices. They are essentially statistical distribution of that, right? And so if we're looking at this plot where we are essentially looking at the uncertainty of each mixed state and the entropy of each mixed state, you can imagine that each of these points, we have a bunch of mixed state because there are going to be a lot of mixed state at the same uncertainty with the same entropy. So what you want to do to basically say, I want to make the high entropy limit, you want to make, so let me do this first. That it's very annoying. There you go. There is the pointer that keeps disappearing. Okay, so you want to basically look at what happens at a high entropy. And the way that you go and look at it, you make a transformation that takes states and bring them up and up and up, and you study what happens when you're making that change. You have a couple of ways to do it. What we're doing in the paper is to look at what happens at the Wigner function, for example, or the Husimi function. Now, Wigner function is, maybe you heard it, it's this idea that you have negative probabilities. You have this quasi-probability distribution in phase space that are functions that integrate to one, but there are zones that have negative probability. And there are multiple ways to represent mixed states in quantum states with this type of quasi-probability distribution. The Wigner functions have the nice property that if you make an expectation of position and momentum on this phase space using the Wigner functions, then you are going to get the expectation of the polynomials of position and momentum that are in symmetric order. So you basically take all the permutation of position momentum, you average them out, and now the expectation of that is going to be the classical expectation using the quasi-probability distribution. So the typical way that you do the classical limit is by looking at what happens at the Wigner functions at the Moyal bracket. The Moyal bracket is essentially the corresponding of the Poisson bracket in quantum mechanics and phase space, which is also the correspondence of the commutator in quantum mechanics and phase space. And what happens is that the Moyal bracket will have an h bar as a parameter. And if you take that limit of h bar that goes to 0, the first term, the one that remains, is the Poisson bracket, and all the other things are correction terms of that h bar. And so mathematically, you have Moyal bracket equal Poisson bracket plus terms in h bar. You make the h bar that goes to 0; those terms disappear, and now you have recovered classical mechanics, right? That's basically how you get the classical mechanics. What we want to show is that when you're making these steps that you're going to go to higher and higher entropy, we're keeping h bar fixed, but these terms that will go to 0 as you take h bar goes to 0 are also going to go to 0 when you make this stretching go to infinity, when you make the entropy, this transformation become more and more. So you're going to have some kind of stretching coefficient gamma that tells you how high in entropy you're going to go. the Moyal bracket is going to be Poisson bracket plus these terms with this gamma, and then you're going to go into share, oh, as this gamma goes to infinity, these terms are going to disappear in the same way that they would disappear if you made h bar go to 0. That's basically how it works technically. And so what we need to find is what we found in the paper. We found an example of a transformation that does this. We check that make all the entropy go up. We checked a bunch of the different things, and then you say, okay, instead of thinking of h bar going to 0, we can think it as we are making this stretching, this higher and higher, going to higher and higher entropy. What happens to the Wigner function is that the Wigner function gets stretched in position and momentum, like you would expect, because you are basically, to increase the entropy, we're stretching position and momentum and making these distributions more and more spread. But it doesn't only get stretched, it gets also convolved with a Gaussian, meaning that the areas of negative entropy, they do remain small, and in the limit, they actually become positive, or they become non-negative. And this is because there is another function, quasi-probability distribution, which is called the Husimi Q distribution, which has the property, instead of giving you these products in these symmetric orders, there are other orders, the normal order, then the anti-normal order, that are in terms of the ladder operators of the what's it called, of the harmonic oscillator. And as I said before, the anti-normal order is the one in which you get the nice commutation relationship. And so the Husimi Q is the one that sort of sees this transformation. The only thing that it sees is the position and momentum get stretched. Now, the Husimi Q has this interesting property that it's still a quasi-probability distribution, but it's non-negative. There are no negative areas. It's still a quasi-probability distribution because the points are not independent event like you would have in classical mechanics. That if you prepare one, you kind of have to prepare another one anyway. So what happens to the Husimi Q is just that it gets stretched. So it's always positive, and it just gets stretched. And in the limit, the Wigner function becomes closer and closer to the Husimi Q. So you have guaranteed that the Wigner function becomes less and less non-negative, because in the limit it's going to become always non-negative. And the expectation that you would have on the Husimi Q becomes the same as the expectations that you would have in the Wigner functions, which means that if you make now the expectation in symmetric order or anti-normal order, it becomes the same. So the ordering of the operator doesn't matter anymore, and that tells you, okay, then the position momenta are going to be commuted. So there are all these nice insights that sort of all work together, and you know, it would be a lecture in itself. So I hope that at least this gives you a better idea of how it works at the technical level.
Moving on to the next question from Isaiah. Are you assuming that the universe can be neatly divided into regimes, classical, quantum, classical, etc.? Can these models be applied to intermediate regions, say between classical and quantum?
Right. So the assumptions are strict. The universe is not, right? So you could make the case that both the classical assumption and the quantum assumptions are like even the idea that you have these system that you can completely isolate them, right? It's of course it's an assumption. It's never going to work. And the thing that at a physical level I'm not so clear is whether these assumptions that are essentially simplification assumptions, right? Because you say, for example, I have a Hamiltonian evolution means complete isolation. It's never going to work. It doesn't exist, but in a lot of places it works. If I have quantum states, for example, I can study a proton or an atom as a single quantum state, as a single wave function packet. And I can only do that if I assume that the internal dynamics doesn't matter, and if all the processes that I'm studying do not elicit the internal dynamics, it doesn't matter. So the atom can be studied as a whole, the proton can be studied as a whole. But then, of course, these are idealization as well. Like, there are definitely regimes in which you can't study a proton or an atom as a single object, a single quantum object. It's going to be a composite object. Quite frankly, is an electron a composite object? Is it an assumption that it's in a composite object? I don't know, right? We assume it because in all the processes that we've studied, that's a valid assumption. Whether it's a real assumption, we don't know. And so the universe, it's what it is. It's a complete mess. And then we find some, systems that in some cases we can model with these assumptions. Some systems seems to be, following the assumption better than others, but we can't guarantee that the assumption is always going to be valid. We cannot guarantee that electron do not have a substructure and therefore they're always be described as a single quantum object. I cannot guarantee that during an emission process, where a scattering process, when an electron emits a photon or stuff like that, there is no intermediate things where you don't really have an electron, don't really have a photon, but you have something in between. I have no idea. Maybe we're gonna, maybe for quantum gravity, we will need to have some of that description. I have no idea. So what I know is that there is a universe, there are some models that I make under simplifying assumption. To me, the open question is whether the assumptions are actually needed to be able to create the theory. So it could be that since I want to make my theory rigorous and with math and funny symbols and all precise, it could be that at some point I have to make a cut. I have to make a cut that says these are the things that are in the theory, and it has to be a sharp cut because the theory has to be mathematically precise. So it could be that there is no way of doing this without making this assumption that in some sense simplify and in some sense also make sharp the division, for example, between system and environment. Can we define, whenever we're taking a system, we have to define, okay, this is part of the system and this is part of the environment. Otherwise, how can I define a notion of a state? But you could argue that that thing doesn't exist. Like in the universe, there is no such thing as this sharp division. And then you would be arguing that all the physical models that we're doing are always going to be some approximation, because in the process of describing and writing a formal physical theory, we have to make that assumption. So that's the part that, for our philosophers that are interested in that question, and we can make an argument to that all physical theory needs to have this assumption, these assumptions that are always simplificatory assumptions, that would be interesting to me. So I don't know if this answers the question, but these are the thoughts that I personally have in my head.
I can just point out related to that. I mean, just looking at recovering classical mechanics as the high entropy limit of quantum mechanics, then this also implies that you have these intermediate regimes where you, just like in the case of relativistic classical mechanics versus non-relativistic, you can use the non-relativistic equations if you're at 10% or 5% of the speed of light or something, and you can calculate quantitatively exactly how much you're going to be off from the more detailed calculation using relativistic mechanics, and you could calculate at low but not super low entropy using classical equations and quantify how much you'll be off by not using the quantum ones. So this would treat intermediate regions between classical and quantum. The last question in the chat by Arnav. As far as I understand, you say that classical mechanics and thermodynamics are equivalent formulations. How do you incorporate knowledge of the observer in classical mechanics? Isn't thermodynamics a richer theory in that sense? I can see that this can be done for quantum using density operators, but how do you handle this in classical mechanics? And Artem has a few comments, another participant. I can read the comments from another participant related to this question. You can incorporate knowledge of the observer by working with probability distributions on phase space, the usual stuff that you do in StatMech. The great insight is that before going to probability distributions, the symplectic structure already defines entropy.
Right. So let me see. Nice to have the I know I can actually see the question. I can just open it up.
So relating classical and thermodynamics, and how to incorporate knowledge of the observer in classical mechanics.
Okay, so this basically relates to the question of what the actual entropy is described. And this is a whole different kind of work, because there are two ways that that entropy is described in statistical mechanics. One is this Bayesian way of saying it's the lack of knowledge of the observer, and it has some problems. And then there is the other one that is instead characterizing the fluctuations of the system with respect to external interaction. So something is, when you take something and you put it and it increases the entropy and therefore increases the temperature and therefore increases the entropy, it's not that you are, it's the same as, oh, I don't know what's happening, I'm less clueful, is that the external interaction is increasing the number of ways that the system can fluctuate. And there are theorems in statistical mechanics that relates the number of fluctuation to the entropy. And there are when people do thermodynamics out of equilibrium, a lot of the time they actually use the entropy to characterize the fluctuation, and in some sense they're measuring the entropy by looking at the fluctuation. And again, also that can be understood in terms of sort of information ideas, because there is something that is making these fluctuations, and the fluctuation comes from the outside, so you don't know what's going to happen. And so the information that is lost due to the outside fluctuation can still be used to characterize the entropy. So there is this whole kind of worm, and I try, when I develop these ideas, to be as general as possible so that I can keep some of these ideas outside of this kind of worm. And so the way that you do it, that it's similar for both classical mechanics and quantum mechanics, you can relate essentially the probability distribution is characterized, as long as your probability distribution goes down at infinity like an exponential, it's a Schwartz function, you can relate that probability distribution with the expectation of all polynomial of position and momentum. So the way that you say, you could say, I have a probability distribution over phase space, or you could say, I have a way to prepare a system that has all these expectations well defined. So in that sense, you can sort of go back and forth, and then there is no knowledge, because in that sense, what you do in terms of expectation is the same as if it's a Bayesian lack of knowledge or if it's external interaction. And so you can run the argument of sort of the connection between the symplectic form and the entropic structure with both arguments. You can say, I can imagine that my entropy is a Bayesian type of entropy because it's lack of knowledge, or it's because that it's an internal system that it's making my system fluctuate. And in fact, the probability distribution is the exploration of my state in a given delta t that it's given by the time scale of the definition of my microstate. And fortunately, things work out in the same way. And so you can now be a Bayesian and use my argument, or hate Bayesian and still use my argument.
Okay, that also answers the follow-up question in the chat from Artem. It's 11:30 Michigan
Yeah,
time.
yeah, exactly. This is exactly what
Yep.
Artem said. Yes, I need maybe like 1 minute so that I can disappear for 1 second, and I'll be right back.
Right.
Okay, I think I'm back. Okay, yes, okay. So there is the delay on, yeah, so it always scares me. Okay, so let's start the second section. In this session, we are going to go a little bit deeper with the results that we have in classical mechanics for the reverse physics. And this is sort of the, let's say, the only theory where we did the whole approach. And all of the results are there in the book. For the other theories, we have a lot of ideas. For quantum mechanics, probably just a matter of putting them together. It's just that it will require time, and I haven't done it yet. So we are going to go and look at classical mechanics to just, again, give a sense of how the details are going to work here. Okay, so these are the 4 assumptions that we use for to recover classical mechanics. Infinitesimal reducibility, we briefly talked about it before. You have a system, and the system has an extension, is a finite system, and then you imagine that it can be broken up into little smaller and smaller pieces, and then studying the whole is equivalent to studying the part. We're not going to go through the details of much of that assumption, but it's always in the back of our head. The other idea is that the system is described by a series of independent degrees of freedom. And again, describing exactly what that means, it's a little bit, I mean, it requires some time, but basically this assumption of, I should say that the assumption of infinitesimal reducibility basically tells us that the classical state of a classical full system is a distribution over the state of the infinitesimal parts. And so the particles in quantum mechanics, you can think them as these infinitesimal pieces that we're decomposing the system in. Then, of course, they are going to become the center of mass for the position and momentum of center of mass for a class of systems that are rigid, that have particular properties. But in a most basic sense, that's what we get when we assume that we have infinitesimal reducibility. And we also get that the states are essentially point on a manifold, because we're assuming that the variables can be are ranges that can become smaller and smaller and smaller, and therefore we're going to become real valued quantities. So the real valued quantities on the manifold you get from the assumption of infinitesimal reducibility. Then you have the assumption of independence of the degrees of freedom, which one might think that you already have in a manifold, because locally, it's the product of real line. But actually, from the physical perspective, the requirements of independence is stronger, because we have units. So if you define units on one quantity, then the other quantity can only be independent if the unit can be chosen independently. If it cannot, they're not independent. So if we have position and velocity, once we fix the unit of position, well, the unit of velocity is no longer independent from the unit of position. So they're not independent in a physical sense, not because you can't pick the 2 values that are different, but because when you define one, you have to define the other, or you can't define one without defining the other. We can't define velocity without defining position. It just doesn't work. And also, we need to be able to give account on these configurations. We need to have an entropy that it's invariant under changes of frame, because otherwise we wouldn't be able to talk about these descriptions as being really independent. They're independent because we don't care who is making the how you're describing it. And so there is a lot more physics that is actually like that you'd think that would be there in the assumption of independence of degree of freedom. And that's how you recover conjugate variables, where you cover the symplectic form and a lot of stuff like that. You recovered from this assumption of independence. Then you have the assumption of deterministic irreversibility, which we already talked about before, which can be formulated in different ways, that the entropy is conserved, the count of states is conserved, and so on. And if you take this assumption together with the first two, then you're going to recover Hamiltonian evolution. And then we also have this assumption of what we call kinematic equivalence. This is a little bit the trickiest one to understand. The idea is that the kinematics of the system, the trajectory is in space-time, are enough to reconstruct the dynamics. So we're going to have these two pictures of looking at things, position and velocity and position and momentum. One just describes what we see, position and velocity in terms of some coordinates and how they evolve in time. And instead, the dynamics is going to be the momentum, the energy, the forces, the causes of motion. And we need a link to connect the two things. And this is what the kinematic equivalence does. And this is what allows us essentially to recover the notion of inertia, of masses, and of scalar and vector potential forces. And this is basically the picture that we have in our head, that if we assume infinitesimal reversibilities plus independence of the degree of freedom, we get the whole notion of classical mechanics. If we assume also deterministic and reversible evolution, you get Hamiltonian mechanics. If you assume that you have kinematic equivalence, you get Newtonian mechanics instead, and the intersection between the two is Lagrangian mechanics. And we leave the space out for statistical mechanics, where we where there is a lot more going on than just looking at trajectories, because of the trajectories so spread out in phase space. So these are the four assumptions, and this is how there you go. How basically they play around with each other. So as I said before, infinitesimal reducibility plus the independence of the degree of freedom, you're going to recover the notion of classical phase space. With classical phase space, adding deterministic and reversible evolution, you're going to get to Hamiltonian mechanics. Then you are going to add the kinematic equivalence. There are two ways to implement it mathematically. One is what I call weak, which basically just means that you have an invertible function between between momentum and velocity. And let me again get this pointer option fixed, because otherwise the cursor becomes invisible and it annoys me. And so if you assume that there is this way of recovering momentum from the velocity, you're going to be able to get to Lagrangian mechanics. The full way to implement this assumption is that since velocity is a linear under transformation of position, and so the momentum, they both have a linear structure. So the correct way is to link these two with a linear structure, because they're both linear structure on the same quantity. And that's basically meaning that you have a relationship between position and momentum, but that position is linear. And once you have that, you basically constrain the system to be one with massive particles under potential forces. And the metric tensor becomes that linear relationship between position and momentum. And now I'm losing voice, so I hope I will have voice for the rest of these 50 minutes. Okay, so again, in the spirit of we want to be able to have a lot of ways to look at things, just to let me, this is what we had before. This is what we had before. Also, the infinitesimal reducibility, there is a couple of ways to look at it. The kinematic equivalence, especially the full kinematic equivalence, has many equivalent ways to look at it that are very interesting, that they are equivalent. And it's probably even an area where probably even more work can be done, because I still have not gotten over it of how some things are surprising. So as I said, it's basically assuming that there is a linear relationship between conjugate momentum and velocity. And then assuming this is essentially assuming that there you have massive particles under scalar and vector potential forces. So the fact that these two things are the same, and this mathematically you can show very easily, is kind of mind-boggling. And but there are other things that are sort of similar, that are sort of surprising. That if you're at each position you assume that there is a local inertial frame, then that's the same assumption. Or that the position fully defines the units of all state variables, and therefore an inversible transformation between momentum and velocity, then again you get the same thing, which again is surprising. So we're not going to look at that too much. What we're going to look at is the action principle. And I'm really losing my voice now. This is not good. Okay, so I'll try lowering my voice. I don't know if I'm going to hold. Well, okay, so the required background to look at the action principle is that we're going to have some equations from Hamiltonian mechanics, which are the usual one. Hopefully you're familiar with them. From Lagrangian mechanics, we use the notion that the action is the integral of the Lagrangian over a given path. So we have a path gamma over position, and we are going to have an action. It's going to be the integral of the Lagrangian, which is a function of position and velocity and time. The actual evolution are the paths that take the action and make it stationary. So the variation of the action is zero if we vary the path. And then the Lagrangian is the Legendre transformation of the Hamiltonian. So Lagrangian is position times velocity minus the Hamiltonian. We are going to use some vector calculus ideas, because what we basically show is that the principle of stationary action is just an application of vector calculus. Given a vector field V, a field line is a line that is always tangent to the field. Given a vector field V, we have a divergence that gives us the flow of the field through an infinitesimal closed region. And the divergence-free field, a divergence-free field is a field for which the divergence is always zero, admits a vector potential A, such that B is the curl of A. So this is what we have for a magnetic field, for example. It's going to be the same thing that we're going to have for the action principle. So the first thing that we should say is that when somebody is introduced with the Lagrangian, is told that the Lagrangian is the difference between a kinetic energy and a potential energy, and this does not always work. So this is the Lagrangian for a charged particle in an electromagnetic field. This is the kinetic energy. This is the potential energy. This part is neither kinetic nor potential. If we go to field theory, you're going to have mass terms and interaction terms. Are those potential or kinetic? It's all this idea is sort of ill-defined. That's what should tell you that if you want to really understand this action principle, you have to abandon this simple idea and find something that works more in general. So what is the correct setting to understand this the action principle? Is going to be in what is called the extended phase space. So we have position and momentum here. So in this plane, we have all the states. And then we have here time. And so states are going to be flowing in time. And at each point, we are going to have what we call a displacement field that is going to tell us how we're going to be evolving time. It's telling us how we move into time. These gammas here are the actual evolutions, and the actual evolution of the system, you can imagine them as being position and momentum and time as a function of time. And what is important here is that time plays two roles. First, it can be the affine parameters on the curve. So it tells us how far we are on the curve. So when we are changing this time, we are going along the curve. Or t can be a variable. So if we're changing t itself, we're just going along one of the axes. And this is important because a total derivative is meant to be a derivative in time over the evolution over a path, while a partial derivative in time is meant to be a derivative at t with p and q constant. So those are two different things. But the thing that is important here is that the evolutions are field lines, and so they're always tangent to the field. That's the important thing. Now we're going to add the assumption of deterministic irreversibility, which here is implemented by just saying that if you have a closed region, we have a potato, then as many states flow in and as many states flow out. So the surface integral through that closed surface is going to be 0, which means we're going to have a divergence-free field. Now, if we have a divergence-free field, as we said before, it emits a potential. This theta is going to be our vector potential, and we're going to stick a minus sign in front of it to match the convention that we have in classical mechanics. Once we have that, we can say, okay, how can we characterize this vector potential? Well, it's a vector potential, so it has a gauge. We can use fix the gauge to make our vector potential look nicer. And the way that we're going to fix the gauge is to take this component as setting to 0 by making this transformation. Then another thing that we can do is calculate the component st, which is going to be partial p theta q minus partial q theta p. And this has to be equal to dt dt. But what needs to happen is that dt dt is going to have to be equal to 1. So we want this component to be 1. Now, theta p here is 0, so we don't have this part. So we just have that the partial p of theta q is equal to 1. So without loss of generality, we can just set this theta q to p. And so now our vector potential is p, 0, theta t. These are the components. And this is an arbitrary function. And we can just rename this to minus h for no apparent reason. And so without loss of generality, under the idea that we have 1 degree of freedom and we have a deterministic reversible evolution, we can say that the displacement field is minus the curl of a vector potential, and the vector potential has component p, 0, and minus h, where minus h is an arbitrary function of position of momentum and time. Once we have that, we can say, okay, let's go and actually calculate this curl of this theta. And if you do the calculation, what you find is you recover Hamilton's equation. For example, theta t here is minus h. So you have minus the partial p of h, but you have another minus here. So you get the same thing. Theta p is 0, and this goes away. So you get the same thing. So what we already have derived, just by this simple assumption, we recovered Hamiltonian mechanics with 1 degree of freedom by saying that we have deterministic and reversible evolution. Good. Now we have this vector potential. What do we do with this vector potential? Well, it's a field. We can define a line integral. Why not? So we take a random path gamma that is not necessarily an evolution, but we still want it to go forward in time. We don't want it to go back because those evolutions do not make sense and we wouldn't be able to parameterize them with the time. Okay, so these are the components of theta, p0 minus h. And the gamma, like this, the infinitesimal displacement over gamma, can be written as dq dt, dp dt, dt dt multiplied by dt. And now we have just the scalar product. So we have p dq dt, so it's momentum times the velocity, 0, so it's going to be 0, and minus h times dt dt, which is 1, so we have minus h. And you can recognize that this is pv minus h. This is a Lagrangian, except that we have to assume that we can expect that we can express this p in terms of position, velocity, and momentum. This is where the kinematic equivalence assumption comes in. Otherwise, we would have a Lagrangian with a function, but it's not a Lagrangian because it would be a function of position, velocity, momentum, and time. Now, because we have key, we can explicitly write it is in terms of velocity. And now this is the action. So what we see is that the action is the line integral of the vector potential of the flow state. So we know what the action is. It's the line integral of the vector potential. The vector potential is unphysical because we have fixed the gauge. We could change the gauge. We can do different things. That's why the Lagrangian is not unique. And that's why the action itself tells you nothing. The action, you don't go and measure the action. Like there is no physical meaning. If I have a path, the action is 5. What does that tell you? It tells you nothing. So now we want to understand what is the variation of the action. And what we can look at is we have a path, we have a variation, and we're going to have some flow that goes through the surface that is in between the path and the variation. So we have the flow, and we define it as minus the integral of s with respect to the surface. Now, s, we saw before, minus s is the curl of theta. So using the Hamilton equation, we can make this step. We put it here. But this is the surface integral of the curl. We can use the Stokes theorem. And now it becomes a line integral on the contour of theta. So it's the line integral of theta along this line and along this line. Now note that we're taking this line in reverse. So it's going to be the integral of over gamma minus the integral over gamma prime. This is the variation of the action between the path and the variation. So this is the variation of the line integral of the vector potential. This is the action. So this is the variation of the action. So the variation of the action geometrically tells us what is the flow of states through a path and its variation. And that is physically meaningful, because how many states go there, what the flow is, that's telling you how the system is evolved. It's characterizing how the system behaves. So this is the interesting bit, is that the action itself is unphysical because it comes from a vector potential, but the variation of the action, because we're doing the Stokes theorem, becomes something meaningful and geometrically interesting. Okay, so now why does the variation of the action, why is the variation of the action 0 along an evolution? Well, suppose that gamma is an evolution, right? And now what happens is that gamma is a field line of the displacement field, so it's always tangent to gamma. If our variation is small, right, then this infinitesimal surface will also be tangent to the flow. And so there's not going to be any flow that goes through the surface between the path and variation, and therefore the flow is going to be 0. So if I have a path and I make a variation of the action, then I look at the flow is going to be 0 because the field line is tangent to the flow. Conversely, if I have a path and the path is not an evolution of the system, then I can always find some variation that catches the flow. So if my path was like this, I make a variation on this side, we're going to catch some flow. If I catch some flow, then the variation of the action would not be 0. And the path would not make the action stationary. So the stationary the action is stationary over and only over the evolution, precisely because the evolution are always tangent to the flow, and the variation of the action measures the flow through the path and the variation. And if the flow is tangent, then there is no flow. And those are the only lines that have that. So what is beautiful to me is that something that is absolutely mysterious, that is said when you do physics, you don't know where this comes from, is justified by things like that nature is economical or some other stuff like that. Actually, it's a very, very simple geometrical representation that only requires vector calculus, which is something that in physics and engineering and so on, you need to do E&M. So there is nothing extra. And so this is where is it? Okay, this is how it works. You assume that you have 1 degree of freedom of classical space, you have deterministic irreversibility, you have kinematic equivalence, you get the principle of stationary action. But the thing that is even more interesting to me, if we remove this kinematic equivalence, right, we are still going to have a pseudo Lagrangian. It's just not going to be a function of just position and velocity and time, but there's going to be position, velocity, and momentum and time. And so this interpretation of the action principle actually still works, and you still have some type of action defined, which tells you that really to understand the action principle, the action principle is really a property more fundamentally of Hamiltonian mechanics than of Lagrangian mechanics. And Lagrangian mechanics just makes it more specific for some cases where you have this kinematic equivalence, and so you can express the momentum in terms of the velocity. So to really understand things, even in Lagrangian mechanics, you should really understand Hamiltonian mechanics and the notion of phase space. Okay, so this is for 1 degree of freedom. I want to go through a little bit more quickly on the multiple degrees of freedom, because it's nice to understand how things generalize, and it's also nice to see how the math works, and it sort of gives you a sense of something that we're going to be talking in other presentations, that sometimes the math that we have a given mathematician, in this case differential geometry, it's not quite spelled out in the way that we would need it to understand the physics. And it is possible to sort of reshuffle things around so that the physics is more brought up. So I'm going to show you sort of how I think of the differential geometry and the notation that I use, that it's a much similar way of the Einstein component notation that we typically use in general relativity. And I think it sort of gives you a flavor of what is required to sort of make these insight more general and more precise. So here we will need some elements of differential geometry. If you have done a special general relativity, it would help, because you will be familiar at least with some of this notation. And if you don't, I'll just try to give you a sort of a high-level understanding of what these pieces are. So in differential geometry, you have something called a differential form. So a differential n form is something that takes n vectors. It's a function. I give you some vectors, and it returns a number that depends on the volume that those vector, or the parallelepiped that those vectors make. So, for example, you can imagine that I have work. Work takes a line, right? I have a path, and it tells you what is the work that I need to take from taking the particle from one side to the other. And we can think that as the integral of the path of infinitesimal contribution of work. And this is the number that we want, this infinitesimal contribution. And this can be seen as a force applied to an infinitesimal displacement. So this infinitesimal displacement is the vector that we're giving to the force, and the force is a function that takes a vector, and it gives us the little amount of work, the infinitesimal amount of work that we need to sum up. Now, F now is a one form, because it's taking a vector and it gives us a number. Now, if you study differential geometry, you will see that typically these dx's are the basis of the one form. I'm not doing any of that. This is the standard way that you do. It's much more closely of what we do in again in vector calculus. So these displacements are vectors, and we can give vectors to functions of vectors, which are the forms, and we get numbers. Same things, you can imagine a magnetic flux. A magnetic flux takes a surface, and you want to know what is the flux that goes through. Well, that's going to be a surface integral of some infinitesimal contribution, and the infinitesimal contribution are going to be given by the magnetic field and the two vectors that give you the infinitesimal area element. And again, what I'd like you to think about is magnetic field not as the vector that is perpendicular to the area element, but as a function that takes the two direction of the area elements, the two vectors that make the area dimension, and give you a number. Why you should think like this? Because this is the way that things generalize. Even when you are in special relativity, you think as the electromagnetic field as a rank 2 tensor. This is what you're doing. You're giving it two vectors, and it gives you a flux, or it gives you something else. Right? This is how it works. And same thing, if you have a mass, if you have a volume, you can say how much mass there is inside there. That's going to be a volume integral of the infinitesimal contribution of mass, and that's going to give you by a mass density times the volume of given by 3 vectors. So again, I encourage you to think as a mass density as a function that takes 3 infinitesimal displacement, 3 vectors, and it gives you the infinitesimal mass. Once you think it like this, you can see the pattern, and now the pattern works in any generality of any surface on any dimension. So you have an n-dimensional space, you have an integral of a function that is defined on an m-dimensional surface, and you can think that as made of infinitesimal contribution of an m form over m vectors. So pseudo-vectors are really 2 forms. That's how you should think about it. I kind of wish that even when we did vector calculus, we did it in this notation with this idea, because these are the things that generalize, so it makes it easier for later. But there are some advantages when you're only stuck in 3 dimensions with vector calculus. But then there is the notion of an exterior derivative that is basically a generalization of the gradient of and the divergence of the curve. And it can be defined on, for example, on a simple scalar function. And this basically is the gradient. It can be defined on a single 1 form, and it gives you a 2 form, which is the curve. Then it can be defined on a 2 form, and then that's going to give the divergence. So if this were the magnetic field, then this would be the divergence of the magnetic field, and this would be 0, right? And we are writing the magnetic field with this different notation. Once you have internalize this, and of course you're not going to be able to internalize it in the 2 minutes that I'm explaining these things, you have generalized properties. So you have a generalized Stokes theorem that whenever you have an integral of an exterior derivative of something, then you can take this integral and make it on the boundary. For us, it's still going to be a vector potential, so it's not going to, you don't have to understand the general case, but the important thing that this works. And also what gets generalized, if I have a 2 form, that it's an exterior derivative is 0, which means it's the divergence is 0, then it admits a vector potential. So the point of doing all this is to be able to say the same thing that we had, that we have a 2 form, in this case was the flow, it has a divergence, some type of divergence 0, then it admits a vector potential. So that's what the math that we have here allows us to do. And so the way that this generalizes is now we don't just have a Q and a P here, we have all the possible degrees of freedom, and again we have a flow in time. And then we're again measuring the flow, but we're measuring the flow still on area, not on volumes, because we want the flow of a configuration of each degree of freedom. That's what we are going to want to characterize. And so it's a function of 2 vectors, because we're still going to characterize areas in terms of 2 vectors. And we want to, whenever we have 2 things, 2 vectors, we want to say, okay, how much flow do I have through a surface that it's made by the 2 infinitesimal vectors. So we can do that. And what we find is that if you assume deterministic and reversible evolution, we kind of have a sort of a divergent-like thing on time, meaning that the configurations are conserved through time. So if we make this variation of the flow along time, we need to have a 0. And this captures the assumption of thermic reversibility. For the independence of the degree of freedom, the configurations are conserved across degree of freedom. So if I have a little bit of an area that is defined on a degree of freedom and make a modification, then those configuration has to be the same whether I shift over an independent degree of freedom. And this means that now the partial, these derivatives in terms of positional momentum also are going to give me are going to be 0. What is interests me mathematically is that if now we have both these conditions, we have this idea that the form is closed and therefore it will emit a vector potential. But you see that, well, mathematically, this is a nice and compact single requirement that you're making. You're making 2 different mathematical requirements in terms of the physics. So if you fail, for example, to be deterministic, but you still have this degree of freedom, there are some things that are going to survive while the other one does not. So this is exactly the thing that you have to do in reverse physics, is understanding exactly how the physical assumption map to the math, and sometimes it's not a neat map 1-to-1, because because it isn't. There is no reason why it has to be always at the same time. So this is why I wanted to look at to show you the details of multiple degrees of freedom, because you can see that there are things that are sometimes not nice, and then you have to be able to understand it and deal with it. But now, once we have this assumption, then we can basically go and say essentially what we did before. This form is closed, it will admit a vector potential. And then, again, without loss of generality, you're going to be able to see that this vector potential has the P, the sort of corresponded conjugate momentum in the position. So these are n components of position, and they're going to be the n momenta. Here is 0. These are the component of momentum that are all 0, and the time component of the vector potential is T minus h. So this, if you studied again relativity, this is basically the form momentum, right? These are the components of momentum, and this is minus the energy. There is just no C here, but it's basically the same thing. Now, if you do the calculation, and I'm not going to do that, you find that omega can be expressed now in terms of h. This is basically so this is the symplectic form. It's a 0 identity minus identity 0. If you have studied some symplectic mechanics, you recognize it. But then there are the time components. The time components are given by the entropy. So the mathematical formation is a little bit different. Now we have to sort of relate the flow with this. So the displacement field with the flow, right? So before, in 3 dimensions, the flow and the displacement field were essentially the same thing. We were doing a surface integral of the displacement field, which was also the flow. Here, the flow is sort of a one-dimensional vector field, while this the displacement is still a one-dimensional vector field, but the flow is a two-form. So the relationship that you need to have between the flow and the displacement field is that if we're taking the flow, and one of the vector that we're giving to calculate the flow is the displacement field, then the flow has to be 0, because the flow because the displacement field has to be tangent to the displacement field has to be tangent to the flow. It has to contribute no flow, right? And so for whatever W that we put here, when we go and calculate the flow from a surface where we're going across the path, this has to be 0, which means that if for every WB this has to be 0, then this has to be 0. Like the constraint that we're making, the relationship between the flow omega and the displacement field S, is that if we take this and contract with the first index, then we need to have a 0. But since there is a B that is free here, we are going to have a 2n plus 1 constraint. So this is actually giving us 2n plus 1 constraint. And if you make the calculations, what those constraints become, they're going to become Hamilton's equation. So again, in sort of a similar way, we have used the deterministic and reversible evolution and independence of the degree of freedom, and we have recovered Hamilton's equation. And once we have, again, these relationship, we can go, we have a vector potential, we can define the integral of the vector potential, and the integral of the vector potential, again, we're going to find that it's the action. So the action is, again, the line of the potential of the vector potential of the flow. And then, again, we are going to calculate the variation of the action, and we're going to find that the variation of the action is actually the flow between the trajectory and between a path and its variation. And the variation of the action are going to be is going to be 0 if and only if we have a path that it's always tangent to the flow. Because if we want this to be 0, then this has to be 0 for every variation, which means for every one of these. But now what we're going to have is that if this part here has to be 0, no matter what this is, then this part here has to be 0. So we have to, this has to be 0. But the only direction that kills the flow, that for which this equation is valid, is the actual evolution. So you can recall all of that. So again, the important bit here is that the math becomes more complicated, but the physics does not. The conceptual parts are still the same. It just becomes a little bit more difficult to map the physics to the math, because the math is more advanced. You need to know the more advanced math, but there is a way to look at the advanced math in a way that it's physically meaningful. And a lot of the time, when you just open up a math book, the way that things are set up, they're not there to give you a picture that it's useful for physics. It's a picture that it's useful for mathematicians to think about the problem, calculate, and prove theorems. And that's not always the way that we would like in physics. We would like to have definitions that are mapped closely to what we would like. Okay, so this is as much as I wanted to show. And again, if in any of these things, if there are people that want to dig more deeper, we can, if anybody wants, we can set up another live and we can go through more of these. And this is, again, it's all in the book. And everything that it's interesting for me to talk about and discuss quickly, because we don't have a lot of time, it's a connection to relativity. Already we saw that the theta is very close to the form momentum, essentially. So we already are seeing some elements of relativity appearing out of nowhere. The energy is the time component of a covector, right? So we didn't assume anything about speed of light or anything. So what I want to show is that there are some elements of relativity that essentially appear out of nowhere. And because, again, the laws and these assumptions constrain the law a lot more than you would expect at the beginning. And this is part of the fun in reverse physics, in realizing that the physical problem is a lot more constrained than we think it is. And so these are the things that I will use from relativity. We are going to have space and time coordinates, and they're grouped together. And typically you group them with the time rescaled by the speed of light. So this is units of distance, and then you have the position. There is a metric tensor that defines the geometry of space-time. Again, I want you to think as a tensor as a function of two infinitesimal displacements. So a metric tensor takes two infinitesimal displacement, and it gives you the length of the two times the cosine of the angle between them. That's what it does. We are using the minus plus plus notation because it's the one that physically maps better to the thing that we do. So the unit distance defined by our metric tensor is going to be dx squared plus dy squared plus d squared minus dt squared, at least locally. And then we're going to have an energy and momentum, and these are grouped together in the form momentum. So we have minus the energy over c and the pi. So again, note that this c here is because there is a c here. If we define this as a t without the c, this would just be minus e, and so it would be even more similar to what we were doing before. But you know, it's just a matter of how convention of the units, how you want to define things. The other thing that you have in relativity, hopefully you know, you have a forward velocity, and the forward velocity is the velocity with respect to proper time, which is the time in the rest frame, and we use tau to calculate it. And because we're using the minus plus 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 signature, the norm of a forward velocity is minus c squared. So u alpha is going to be our forward velocity, which is the derivative with respect to proper time of the position and the time. And the norm of the forward velocity is going to be minus c squared. And for a free particle, you have the relationship between the forward momentum and the forward velocity, which is the forward momentum contracted by with the metric tensor is going to give you the upper version of the forward velocity, which is basically in our case just changing this minus e into a plus e, and this is going to be the mass times the forward velocity. So these are the pieces that we need from relativity, which of course, if you haven't seen them, you're not going to learn from now, but at least you know that you don't know them because you don't have the background. Okay, so Let's say that we want to extend Hamiltonian mechanics to handle change of coordinates that mix time and space. Okay, that's what we want to do. Then, of course, our position now we need to include t and qi, right? And an evolution on t on an evolution instead of describing as t. Like, we do not want t to be the parameter of the evolution anymore, because we don't want it to be special. Then we are going to have an affine parameter, right? So we separate the time the variable from time the parameter, and now the parameter is going to be s. So when we're going to make a change of coordinates, we're going to change this t, and we're going to mix it with this q, but the parameters remain the same. And the parameter is an absolutely unphysical quantity that we could rescale however we want. It's just a dummy variable that we use. Right? It doesn't have any particular physical meaning unless we pick a particular meaning. So in every frame we could choose s to be t, right? But when we change a variable, we keep s the same. So otherwise we just make a mess. Now recall. Oh, now we are going to need the coordinate, the conjugates of t and qi. And we know that the conjugate of q are the p's, but the question is, what is the conjugate of t? Like, how do we find it? Well, we saw before that when we had our vector potential, p was here, and minus h was the time component of the covector. So we know already that the minus h is a time component of the covector, and during coordinate transformation, this is going to mix with these exactly like the time component of a covector that is only defined on position and momentum. So we only have one way to fix the conjugate. The conjugate has to be minus e, because otherwise when we make a transformation of this, it's not going to be matched by a transformation of this, and we're not going to preserve the fact that deterministic irreversible evolution is the same in all frames. It just becomes a mess. So you need this, and now what you can write is the Hamiltonian mechanics on the phase space extended both by time and energy, right? So you have 4 variables now, t, qi, e, and p. You have what is called the Hamiltonian constraint, which you can use to create, to write the laws of evolution, but it's also a constraint. It's not a conserved quantity like the Hamiltonian, that it's something that you can set it whatever you want at the beginning and it just gets conserved. No, this has to be the same value for everything, because what's going to do by being a constraint is going to be able to fix the relationship between energy and all the other variables. So the Hamiltonian, the standard Hamiltonian that tells you how things evolve in time is essentially hidden in this constraint. And what's nice about this constraint is that now it's invariant. And one of the reasons why you prefer Lagrangian mechanics in a relativistic framework is because the Lagrangian is invariant and the Hamiltonian is not. But if you have this constraint, now this is invariant, and you can start thinking about symmetries in terms of Hamiltonian mechanics instead of Lagrangian mechanics. So it has a nice features to it. Okay, so one of the things that this explains is already, we see that there is this minus sign that comes in from the degree of freedom in position and the degree of freedom in momentum. And the way that I think about it, this is, again, position, the 2 different degrees of freedom are orthogonal because they implemented at different states. They are independent degrees of freedom, and therefore I have a plus sign between these 2, right? So it's like as if I had a Pythagorean triangle, right? These things are orthogonal, meaning they're independent. And then if I have a surface that sort of spans the 2 surfaces, I just using the Pythagoras triangle and get the sum of the 2 areas. Now, what happens is, why do I have a minus here? Well, if I have a minus here and I want to still think about my Pythagoras triangle, what I just need to do is take this and bring it on the other side. And what this is telling me, which is, of course, very true, is that state must be defined at equal time. So it is not, if I have a region, like if I have an interval of position, that's going to define different types of initial condition, different type of configuration, different types of like a number of states. But if I have an interval of time, I'm not creating more states in time. Like it's always the same states that are evolving. So the form that sort of measures the flow, that measures the configuration, that defines the configuration and counts the state, has to be orthogonal to the temporal degree of freedom. And so now we still have a Pythagoras diagram, but the omega, the thing that counts the state, is not the hypothesis anymore. It's one of the sides because it has to be perpendicular to the temporal degree of freedom. And again, this way of looking is a lot more geometrical, a lot more physically intuitive, and it's telling you what's actually going on in physics. It's not just a minus sign because it's telling you something. And I'm sure that there are a lot more things that can actually be derived from this in a much more sensible way in things that we are looking at relativity. But one of the things that is clear here is that all of this reasoning comes because we're working in phase space, not just in space-time. And so I'm not going to be able to have the time to go through it, but what really seems to be the case is that this this signature of space-time, it's actually something that it's inherited from state spaces. So at least when you're doing mechanics, the state spaces are more important than, say, the geometry of space-time, because you can recover the geometry of space-time from the geometry of phase space, but you can't do the opposite. So we're starting to run out of time. So I think I'll have to just flash these slides just to see, to show you how nice this old math is. So this is the free particle with an inertial frame, and you see that this is nice and quadratic, and it gives you the correct equation that you would expect. This would be the standard way that you do Hamiltonian mechanics in relativity, and it connects to this Hamiltonian mechanics in the extended phase space. It's just that this is much nicer to work with. Another thing that comes out of the blue is this notion that you can have classical antiparticles. So you typically think of antiparticles being something that you need a quantum field theory for them. And what happens instead here, very simply, is that we have a quadratic term for the energy. So the energy could be both positive and negative. And from the equation, this could be negative. So and the parameterization goes backwards in time. So our displacement field in terms of parameterization goes forward in time for some state and goes backwards in time for some space. You might have heard sometimes, oh, antiparticles are like particles that are going backwards in time. They're not going backwards in time. It's just the parameterization that one would use is opposite with respect to time. And of course, there is since the parameterization is unphysical, you can change what is a particle from an antiparticle just by changing the sign of the parameterization. It doesn't really matter. But again, what is interesting to me is that you can find these relationships in just classical mechanics, classical particle mechanics. Then if you understand them here, you're going to have a much easier time to understand them in field theory and so on. So this is, again, what I want to stress is that a lot of people that look for new theories and so on and say, who cares about classical mechanics? I just want to do my quantum gravity stuff. There is a lot of insight that you can get just by looking at these simpler theory. And it's much simpler to understand things in a simple theory than one so complicated like quantum field theory. So if you get good intuition, perfect intuition in these cases, and you know what carries out, because some of the assumptions are going to be the same, it's just going to make your life easier. And this is how you would recover the standard Hamiltonian. We are not going to have time to look at this, not time to have a look at this either. And so basically, what is important to me is that relativistic mechanics is recovered without any additional assumption. So relativity is basically needed to make density and entropy invariant over time transformation. That's what happened. In fact, I think there should be a very trimmed down version of these arguments where you can really say, okay, I have the probability distribution and they need to satisfy this requirement under coding transformation, and then you're going to get a metric tensor. I still don't know how to do it technically, but I still think that there should be, this is very, very simple. It doesn't even require all the phase space, like it's going to be much simpler. Then again, if you have never seen the Hamiltonian mechanics of the extended space is really a more relativistic formulation. It's kind of sad that it's not more popular, because it's something that even in field theories you can do, and it's been known since the 40s that you can do this. It's just not popular. I don't know why. And again, you can also make some correction of quantum mechanics, but we haven't seen them. I had a whole other section on the directional degree of freedom. I'm not going to have time for that, otherwise there's not going to be time for question. But really, what is important here is that we have done a great deal of work on classical mechanics to understand all these pieces. I consider the reverse physics part of quantum classical mechanics is essentially done. I'm sure that it can be done better. As I mentioned before, there was somebody who approached me to extend the action principle to dissipative systems, to put in the Riemann dissipative functions and stuff like that. I'm sure that can be done. That there could be the link to Newtonian mechanics probably could be done more precisely, but I don't think any of these things will require any new assumption or a new concept. The assumptions that we need are those four: infinitesimal reducibility, independence of degree of freedom, determinism of reversibility, and kinematic equivalence. And again, I personally feel, and all the people that I talk to sort of confirm my feeling, these are assumptions that are understandable at a physical level. They don't feel like very mathematically heavy, and they're conceptually simple. And the fact that you can have multiple ways of implementing these assumptions allows you to get more insight that you can reuse. And so the point is that all of classical mechanics are a consequence of those. And so a lot of the physical ideas that we have in classical mechanics should be just the consequences of those assumptions. So the fact that we have a principle of stationary action is because we have all those four assumptions. And the fact that we have massive particles under scalar potential vector forces is a consequence of all those assumptions. The fact that we get relativistic mechanics is the fact that we are just trying to add the coding transformation. We don't even have kinematic equivalence technically for that. And the fact that we have a phase space and conjugate quantity can be derived by infinitesimal reducible and independence of the degree of freedom. And so this is kind of like one of the things that I care, is that a lot of the people gravitate to interpretation of quantum mechanics and so on because we don't understand the quantum mechanics. What I realized like 7 years ago is I didn't understand classical mechanics either. I now think that I understand the classical mechanics. But if you asked me maybe 10 years ago, before I started thinking deeply about these things, I would have said, yeah, I understand classical mechanics. It just was only afterwards that I started really to ask myself, well, do I know what the principle of stationary action is? Why do I have conjugate quantities? Why do I have Hamilton's equation? Why do I have all these things? And it never even occurred to me that there could be answer to all those things, just because everybody around me would say, oh yeah, it's like that, and that's it. And so there is a lot to understand with these things. There are probably better insights. And I do think that understanding classical mechanics gives you a lot of insights also then on quantum mechanics, because as I said, all these assumptions are going to be there except the infinitesimal reducibility. That's basically the only difference. And so if you understand what those other assumptions are doing, you're going to be understanding also what they do in quantum mechanics. And I think that's basically it. So if people are interested in learning more, and my voice is gone, we could set up an online reading group. If people are interested, we could have that reading group live streamed on the research channel, and we can find a time that works better internationally for people. And we could go through classical mechanics together, or we can also discuss how all these things play in quantum mechanics and so on. And the only thing that I ask, if there is somebody, if somebody wants to do this, or if there are people that I want to do that, I'd like somebody to volunteer to organize, that basically tells me what are the the times that work better for everybody. They call the meeting, they prepare the the thumbnails, stuff like that we need for YouTube. But again, if there are people that is interesting, I'll totally. I'd really like, as I said multiple times, I'd really like to build a community around this project, because there's too much for me by itself, and if we don't have limited resources of image, there's too much that needs to be sort of gone through. And so if we can create a sort of a global online community on this, I think, and we have the technology to do it. So. And again, to learn more is this, and that's basically it. So we'll open up to questions as long as my voice holds. I hope I have voice for tomorrow.
Right. So first question is from Xinyue. Can't we still have non-zero variation if we make an infinitesimal helix around the evolution path?
I don't think it would be a first order variation. I'd have to think about it. Good question. I don't have a good intuition. So so mathematically, the thing works, right? And so you're not going to be able to make a variation that catches flow. If you're making a helix, there are either two things. Either it's not a first order variation, so you can't do it, or even if you do it, the flow is going to be zero. I don't know which one is which. Very great question. You put me on the spot. Nice.
Okay, the next question is from Carlos. In 1 degree of freedom, you had to fix the gauge by choosing a particular theta2. Is it possible to choose other gauges?
Yes. And you might know that the Lagrangian is not uniquely defined by the system. And the way that you change the Lagrangian is by choosing a different gauge. And we have this in the book. There is like a standard gauge, like a standard way to modify Lagrangian by taking a function and taking the gradient of it and do funny things. And we show that that actually is just a change of gauge. And there are more transformations that you can do. And what it has to happen is that all the equivalence Lagrangian should be able to be reached by a gauge change, which also tells me that all the gauge changes that we do in fields have to be connected somehow with these gauges of this vector potential. So in a sense, what we are saying is, in a sense that I don't know precisely how to make, but there should be a sense in which all the Lagrangian theories have to be gauge theories, because just by writing the Lagrangian, you are choosing a gauge.
Right. Another question from Xinyue. Is there reason in this explanation that the Lagrangian has to be a function on position and velocity instead of position and momentum?
So it cannot be just a function. Oh, actually, no, it can be a function of position and momentum, now that I think about it. Ah, okay, so the only way to say that the Lagrangian is a function of position and velocity and time without momentum is if you're able to write the momentum as a function of velocity. So that there is no other way. Like that's really the assumption, and you can show in many different ways that's always the same assumption. You could write the Lagrangian as a function of position, momentum, and time, because you can always write the velocity as a function of position, momentum, and time through Hamilton's equation. So in principle, you could always have a Lagrangian, a pseudo-Lagrangian. Let's call it pseudo-Lagrangian because Lagrangian has to be a function of position and momentum. So you can always write this pseudo-Lagrangian in position and momentum, but then you are always you have to work in phase space. Like it's explicit that you're working in phase space. But that you can do, yes.
Question from Daryl, or comment. To summarize the concept to make sure I get it, given a flow in extended phase space and an arbitrary path, define the action as the path integral of the vector potential of the flow.
Yep.
A path with stationary action is equivalent to the path following the flow. It sounds kind of tautological and makes the principle of least action obvious.
Exact. Yes, you perfectly understood. Yes. So what I say is the principle of least action is a very roundabout way to ask for the paths that are tangent to the flow. That's it. There's nothing mysterious about it. Yeah.
Assuming deterministic and reversible.
Yeah. Assuming deterministic and all the and independence of degree of freedom and all that. Yes.
So there are currently no more questions in the Q&A. There's a lot of enthusiasm in the chat for a reading group.
Yeah, so if you guys are interested, start sending me email and then I'll put you on the Discord and I'll create a channel in the Discord where you guys can figure out how to do it.
Chat Daryl gives a shout out to the Mathemaniacs channel on YouTube, which explains the same concept presented here.
Yeah, he contacted me after he read the paper. There was a piece, somehow he missed the mathematical appendix where I explain everything in detail. And so he contacts me and says, oh, can you it doesn't seem so precise. I said, what is not precise exactly? And then I explain all of this in the appendix. Oh, there is an appendix. It's like in the introduction, I said, there is an appendix for the math. It was funny. But yeah, so he contacted me and he did that. And he has something that I haven't, he has something more because he also links it a little bit to the Northern theorem, which I haven't done. So, okay, for example, that would be somebody wants to help there. There is something, there is a relationship. I have a conjecture on the Northern theorem through this interpretation that I'd like somebody to see if it works or not. So, that there is a possibility. So the Legendre translation is more of a coincidence or it has a more mathematical, physical reason? I think it's more coincidence. So I don't have a way to fully understand geometrically what the Legendre is doing, except then, to calculate that integral. So if there is a more physical reason, yeah, I don't know what it is. But again, the fact that I don't know what it is, it doesn't mean that there is none. The way that you would know if there is one, if you're able to represent some physical requirement more directly with the Legendre transformation. And maybe there is a way to do it, but I don't know that it is. That there is.
Question in the Q&A from Luke. Do you know to what extent the physical assumptions determine the cohomology of the space? Homology or cohomology?
I still, like, to me, homology and cohomology, rephrase it in a way that doesn't use homology, because I get so confused by those mathematical words. I don't have a concrete intuition. Yeah, sorry. There's some mathematical terms that I still, you can put it in the chat. Like, there's still some mathematical term that I don't have a good physical understanding of them, and therefore I always forget the definition. So if you're asking me for that, I don't remember what it is. So if you can make it more explicit, what is it, the thing that you want me to comment on, I'll be happy to do that. This is basically why I started this whole project. Like, I can remember concept very well, but if they don't lock in some level of understanding and they're just mathematical symbol, after 5 minutes, they just go out of my brain. If I understand and I make a physical connection that it's meaningful and practical, then I can never remember it. I never forget it. Like, it's completely built in my brain.
Contact information in the chat. There's we have time, free time. Can we go to the skipped content?
Yes, we can certainly do that. So I can give you a choice. I have the sort of the more stuff on the relativity part, or I have the deriving the 3 dimensions, the fact that the space is 3 dimensional. Is there any particular preference? So basically, right, those are the 2 things that I had.
Request for relativity in the chat.
All right, let's if everybody, somebody spoke up, so let's go to relativity. Okay, let's see, where do we go? Okay, let's see how the Hamiltonian extended phase space works, because I think it's very nice. So again, you have this Hamiltonian constraint that from your purpose works like a standard Hamiltonian. It's just that one of the variables is time. And so you're going to have a change of the time based on the affine parameters. You're going along the curve. The curve is not parameterized by time. It's parameterized by whatever parameter you chose. And so time is going to evolve on the curve. And that's going to be the derivative of Hamiltonian with respect to its conjugate. And its conjugate is minus e. Right? So we're going to have to take this derivative in respect to minus e. So this part is 0. This part is 0. This is the only part that comes. The c, you can take it out. So you're going to have this minus e squared, but minus e squared is equal to minus outside and minus e squared. And so when you take the derivative, you get a minus here, minus here. These go away, the 2 goes away. So you just have e over mc squared, which if you study relativity, you know that that's a special quantity of that. Then you do the same thing with the position. Position with respect to a affine parameter, we are just taking the derivative with respect to p. And so here we basically have a p squared, because this is the only thing that we are deriving. And so we're going to have a 2. The 2 goes away, and so we just have the p over m. So we have e over mc squared, p over m. And there is no time dependence, and there is no position dependence. So these are all 0. And again, we know that there is for velocity, there exists a for velocity and for momentum. Now you can see that this is essentially the for momentum multiplied by m, right? And so we can take this c, put it down here, put the m on the other side. So we just have m dct over ds. And for this, we just have p equals m, the derivative of the position with respect to time. Well, we know what this is now. This is just the for velocity, because this is the for momentum. It's the for momentum times m, and this is the for velocity. Therefore, s here is proper time. So this Hamiltonian constraint has a conjugate, and the conjugate is proper time. So, and you can look at this. This is essentially, it's like a mass term. Like it's essentially p square over 2m. Right? It's like it is a kinetic. It's like a kinetic term. So that's what it is, and I find it very nice that it just comes out. And as we already hinted, like this s is going to be proper time for particle, and it's going to be minus proper time for the antiparticle. Right? And again, if you then substitute the minus c, you can take the minus, put it in the energy, change the sign of the energy, and then change your sign of the proper time, and then you're gonna sort of make the particles antiparticle duality. So that's how it works. And again, it works very simply. It works a lot simpler than. And again, it's one of those things that I kind of rediscovered, and then I found it in the literature, and I kind of understand why this is not taught more. Okay, look, that's fine. We can also correspond to email if you want for that question. Okay, so as I said, like this is in the standard way. This is what you do. you have the Hamiltonian. Now, this is the true Hamiltonian. It's the conjugate of time. It's the generator of time, while this Hamiltonian constraint, in this case, is the generator of the time parameter that happens to be proper time. Right? This is how it's different. But if you do the calculations, you get the same thing. So if you do the velocity with respect to this Hamiltonian and do the calculation, you're going to have this pi over the square root of m squared plus pi squared over c squared. And since the energy is this, well, the energy is basically this rescaled. This square root is the same square root, except that we basically have removed the c squared from this square root, right, and it appear here, right? So what happens is you can think of dqi dt, this term, as being ds dt, how much the proper time changed with respect to t, the parameterization change in t, and then dq over ds. And this is invertible because time always has to be monotonic with respect to the parameterization. We can't go backwards in time or forwards. Like you always, like the path has to be, time still has to be a parameter. If you wanted to choose a time to be a parameter of the curve, we still need to be able to do it. And therefore, the transformation between the affine parameter and time has always to be bijective. It has to be invertible. And this is where, in relativity, we always think of time and space as kind of being interchangeable. They're not interchangeable. Word lines are the things that we want to describe. And word lines have to be curves such that time can always be a parameterization. All the time coordinates can be a parameterization of a word line, while spatial coordinates does not necessarily have to be a parameterization of the word line. And so if you do this and you get the equation from before, this ds dt is just the inverse of dt ds, which is just mc squared over e. And then this e was pi over m. The m goes away, you get a c squared here, and then you're able to get that right away. Yeah, so it's nice because everything it sort of fits, but if you make this break, you can actually understand more about the geometrical structure and what is actually going on. So much so that then you can understand how the standard Hamiltonian is embedded in the Hamiltonian constraint. So if we have valid states, the Hamiltonian constraint always have to be zero, because that's a constraint. It's if you take this 8-dimensional space spanned by time, position, energy, and momentum, right? There's going to be a constraint, so you take a 7-dimensional subsurface of it, right? And so you are on that surface, and so h is equal to 0, but also that is going to give you the constraint between the energy and the Hamiltonian. So both of these have to be true. And now we can, since this has to be 0, and this has to be true, h minus e has to be 0. So let's stick a constant between the two and assume that for now that this has no dependence. Then if this is equal to 0, this is equal to 0. So the Hamiltonian constraint becomes the expression of the energy with respect to the Hamiltonian. And since you have E equal h, now you can go and write the equation on either the extended phase space and recover the equation on the standard set phase space as basically as part of this constraint. So the derivative between time and time is of course equal to 1, and since we have invertible, we have that the derivative in s with respect to p is times ds dt is going to be equal to 1. Using the Hamiltonian on the extended phase space, this is the derivative of Hamiltonian with respect to minus e, but this here is lambda, because this does not depend on e. This is the only e dependence, and so you have minus c times lambda, therefore you just get lambda. And this for dt ds times lambda is equal to 1. So this lambda here is just the inverse of ds dt. So it's basically, this is dt ds. This is telling you how fast the parameterization goes with respect to time. So again, it's a physical quantity. It's not just something meaningless. It has meaning. And then if you do the same trick, you can express dqi dt. You do the same trick of putting the s here, and then you do your derivatives and so on. You're going to recover the standard equation of Hamiltonian mechanics. So the picture of saying I have a Hamiltonian constraint, or I have some Hamiltonian that it's with a square root of a lot more complex, are the same. You can go from one to the other. And again, I like when all the bits of math like that work well. Even more, what's going to happen when you have sort of particle-antiparticles? You have different terms in the Hamiltonian that if you are on this constraint, this function is a lambda, and if you are on this constraint, then this function is a lambda. Right? This is the thing that it's interesting to me. So now that we have particle-antiparticles, you can see that because we had the e square, we can turn that Hamiltonian constraint into actually two constraints with respect to the Hamiltonian. So we're going to have a e minus h1, and this is h1, and a e minus h2, this is h2, and h1 is going to be minus h2, because we had to stick a minus sign here to make it work. And so when you do your derivative in time, right, the lambda that you have in front of this is no longer, which would be this, right? It's no longer independent of e. It is dependent of it. So it gives you some contribution to the flow of time with respect to the parameterization, and that's how you get this to disappear. Otherwise, you wouldn't get it. So it's interesting to me how all these pieces work, and again, there might be, for now, this is just sort of understanding how the mathematical machinery works, which I still think is interesting, but I don't know if there is more than that. And there probably isn't, because again, there is a choice of the parameterization. We could change the parameterization and change the Hamiltonian, and then the Hamiltonian constraint would be different. So then the other thing that you can do in this formula is to make this quantum classical parallel. So we saw that there were this idea of particles, antiparticles, but one of the things that you can note, like this is the Hamiltonian constraint. And now if you've done quantum field theory, this really looks like the Klein-Gordon equation. So we have a momentum operator square here, and this is the nabla. And we have an energy operator square here. This is the derivative in time. And then we have a mass term, and the mass term is here. Like the only thing that you have an h bar here, but again, instead of thinking it here, think of these h bar as part of these operators, because they're part of the energy and momentum operator. Then it suddenly makes a lot more sense. And these minus signs with respect to this, it's because there is an I square of the operator, right? So this h bar shouldn't be here. You should have an I h bar partial in time all square, and then we will get the sign to actually be exactly the same. And so, again, what is the Klein-Gordon? What is the Klein-Gordon in quantum mechanics? Is just the Hamiltonian constraint of practical mechanics. And the same thing, I think I have it later, it works for the Dirac equation. Another thing that it's nice is that you see how you have the Hamiltonian constraint times the wave function. You can do the same thing in classical mechanics with a probability distribution. Because if I have a Hamiltonian constraint and I have a probability distribution, then either I am over a physical state, and therefore the Hamiltonian constraint has to be 0, or I'm not in a physical state, then the probability distribution has to be 0. And so this constraint of Hamiltonian constraints times the probability distribution equal to 0, this has to work in the same way, both in classical mechanics and quantum mechanics. Again, right now, this is at a level of analogy, but I can't imagine that this can't be, we have a more formal theory that it's sort of abstract, and these are just two instantiation of the same idea in both. So ideally, what I'd like to have, and we'll talk about it when we do physical mathematics, I'd like to have a Hamiltonian theory defined on a generic notion of states and processes, right? That then in the classical case, it's implemented in one way, in the quantum case, implemented in another way. And again, there's so many similarities that I can't imagine that this cannot be done. Another thing that, again, connects to gauge theories, this is the Hamiltonian constraint for charged particles. So this is your field. This is the vector potential, right? And this is your charge particle. This Q is the charge particle. And what you find is that M lower U, right, which is essentially the kinetic momentum in covariant components instead of contravariant components, is P alpha minus Q A. So basically, this term over here is just a for velocity term, right? You have 1/2 M U contracted with U, so this is a norm of U, plus 1/2 MC squared. This is the Hamiltonian constraint. This is equal to 0. And so the only thing that this Hamiltonian constraint is saying is that the norm of the form velocity has to be 0, which I find it completely hilarious because it's basically telling us nothing. And then you have the fact that the real physics is hidden in the fact that the form momentum here is not just the conjugate momentum, like the kinetic momentum is not just the momentum, but there's this extra term. And this is where all the physics is, like this term here is all the physics. And the thing that is interesting, I'm thinking about gauge, this part, mu alpha, has to be a gauge invariant term. It's the thing that we measure. Conjugate momentum, we don't measure. And the for potential is also like defined up to a gauge. So the gauges of these two have to be in such a way that when they subtract, you get something that it's gauge invariant, right? So this thing is gauge invariant. These two things are not. Now, again, we can compare to the Klein-Gordon equation of a charged particle. And again, you see that there is this term partial derivative minus IQA. And again, this is called the gauge covariant derivative. And again, we're missing an IH bar here. And so that would make this also I go away. But what would happen is that this corresponds to this corresponds to this. So this gauge covariant derivative is just the conjugate momentum. So when we're writing this Klein-Gordon equation, what we are actually writing is that the norm of the form momentum has to be equal to C. That's all what we're saying. And again, there's so many things that become, like as we pointed out for the action principle, it became like this tautology that you're basically trying to look for the simple thing. Also, this becomes like this. And 10 years ago, I didn't know that this could become like this. And if we keep going and look for simpler explanation, that's the only way that we can actually find them. And again, I understood this, not because I was looking at quantum field theory, but because I was trying to better understand the classical mechanics and its relationship to relativity. So again, the idea that if you want to understand physics perfectly, you just have to go and look at the most complicated theory possible, quantum field theory, because that has all the answer, because that gives us the best description of nature. It doesn't work. You go to the simplest theory, fully understand the simplest theory, and then you go to the more complicated one. Once you fully understand that, once you've completely exhausted all the possible insights that you could get. So this is why I had this this relativistic part and the connection to quantum field theory to sort of hopefully give you that sense. And that's basically it.
All right. At the end of the hour. So I think this is going to be a good place to stop. Thank everyone again for attending today. And we will have the third and fourth lecture at the same time tomorrow.
I really appreciate everybody for putting in the time, and that makes it all worth it. Thank you again for attending. Okay, so the stream is ended. I can stop the recording. And that's it.
So a few people connected, but I think we can end here and you can recover your voice because you'll need to talk for 3 hours again tomorrow.
It's already going better. My instinct is to talk with a loud voice, but yeah.
It's still streaming, I see.
I said end stream. That's bizarre. Okay, well,